Hey folks, welcome. This is kind of weird. I was hoping I was going to be in Oslo at this point in time to present in person, but virtual is going to have to work. For folks who don't know me, I am Scott Hunter. I'm the Director of Program Management on the .NET team at Microsoft. And today I'm here to talk about the journey to one.NET. This has been a vision that a bunch of us on the team have shared for a long number of years, actually. But let's get started, and I've got a couple surprises. I have one demo at the very end that is a special demo that very few people have seen, so you'll be some of the first people to see it, and let's start moving. I joined Microsoft in 2007, and at that time, .NET was only able to really do desktop and web. And then over the years, we've added cloud, mobile, gaming, IoT, and AI, and so we think it's now a platform that you can build anything with. One of the big questions I always get when I talk about .NET is, what's the health of .NET? And I'm blessed because we build a framework and we build the tools. We have a pretty good grasp of what our numbers are. So we have over 1.5 million people that are using .NET Core today, and this is active monthly, not download and run one time. This is showing the last year's Stack Overflow, where we were the #1 most loved framework, .NET Core was. This year, we were the #1 most loved web framework, ASP.NET Core, and the most loved other framework, .NET Core. And then, we open sourced .NET in 2014, which is kind of late compared to most of the competition. But it's been good for us. We've taken over 100,000 community PRs over time. And we are one of the top 30 highest velocity OSS projects in GitHub. We're the top 5 language in GitHub. And performance has been a huge push in the .NET Core space. We're 7 times faster than Node.js. We're faster than Java. We hold our own with things like Go. So, we're pretty good there. And then as you download and try our software out, we actually survey a lot of folks, and what we find is a lot of folks trying .NET are actually young and students. So how are we doing? We're .NET has been around for about 18 years at this point, and we've added 1 million users just last year, and I think that's an amazing feat. 18 years in to still add 1 million users a year. Of those, about 600,000 of those were .NET Core developers, and then .NET Core is the first version that we've supported that does support for Linux and Mac. And last year we had over 1 million publishes to the Linux folder. So people are actually trying that stuff out. .NET Core 3 we shipped in September of 2019. We shipped 3.1 in December of 2019. And it's the fastest version of .NET ever. If you've been using .NET or looking at .NET over the years, our customers typically moved at a colossal pace, 3 or 4 or 5 years between versions. And when we shipped .NET Core 3, within the first 6 weeks, 75% of our customers had actually tried it. And so that's what we want. We want customers to move forward and stay with us faster. Stack Overflow, which a lot of developers use, they migrated to .NET Core 3.1 a few months ago. And they've seen better performance. The performance was so much better that I remember Nick Craver actually posting a tweet saying that some of their systems that monitor Stack Overflow reported it being down when they first switched to .NET Core 3.1 because it was returning the results so fast that the tech thought the site was erring, and so they had to readjust things because things were so fast. So I want to talk about a few things really quick that we shipped at the Build conference a few weeks ago that we put on virtually, and then we're going to talk about what's going to happen after .NET Core 3.1. So just like 2 weeks ago, we shipped Blazor WebAssembly, and for folks that don't know, Blazor is a full stack stack on top of .NET Core. And by full stack, I mean it's basically any Blazor app is a SPA application. And we shipped Blazor Server in September of 2019 along with .NET Core 3. And what it did is it basically made any ASP.NET app that was using the Blazor template into a SPA application. And it does all that by processing on the server. And because of that, it's actually very lightweight. When it renders a page and you do an interaction, we send the interaction back to the server, it re-renders, and just sends the diff back to the client. And so it's one of the lightest SPA frameworks you'll ever use because it doesn't bring down an Angular, a Vue, a React, or something like that. Now, we just announced or shipped Blazor WebAssembly, and that WebAssembly allows us to actually run C# in your browser. And so you can actually write C# code in your Racer pages, and it'll actually just run right in the browser, which means you can take advantage of the local hardware. But it also means you, for the first time, can really build a progressive web application with full offline support in .NET. Because even with the network off, that C# running in the browser, it can do stuff, it can put stuff in local storage. When it sees the network come back up, it can go reconnect, and I might show a little small demo of some of that code. And it's now in all the .NET Core 3.1 SDKs. And it also comes with Visual Studio 16.6. I'll demo things in a little bit. We'll skip that for now. With .NET Core 3 and 3.1, we also brought the last wave of technologies from .NET Framework into .NET Core. And some of those we brought over were WinForms and WPF. We still have we have millions of developers that are actually building these types of applications. And so we wanted to give people a path forward into .NET Core. And the big thing that we just shipped in 16.7 Preview 2 is all of the toolbox controls and the designers available for the customers. So this means if you have a WinForm application, you can now move it to Core, and you can use the WinForm designer for pretty much everything. We have third-party controls coming next. That'll be soon, by end of the year, I hope. But this is in the box today. And if you try the Preview 2, you get all the controls. And then finally, we shipped about a year ago at the Build conference an ML framework for .NET called ML.NET. And after we shipped it, it is machine learning is a complex chunk of tech. And we wanted to go make it easier for customers to go build apps on top of it. And so we built a thing called Model Builder. And that's basically a wizard that sits on top of Visual Studio. And you can select the workload you want to do. For example, maybe you want to classify images, and that's a demo I have, and we might show. You select that, you give us the training data, and then we'll go build a model for you. And then we'll actually stick it into your project. And we'll write the code for you to actually call and predict what something is. And you can just paste that into your application, and you're good to go. And you can really get started in under 10 minutes with this tech. And I still highly recommend it. So all three of these things, the Blazor WebAssembly, the Model Builder, and the WinForm Designer are all in the bits that just came out. And as I said, we'll do a few demos in a little bit. Skip the demo for now. And so it leads us to a point where what we really tell customers is, if you're a .NET developer and you're going to build a brand new application, now is the time to build it on top of .NET Core. .NET Core 3.1 has long-term support, which means it's good for 3+ years of support. It's got WPF and WinForms brought over to make it easier to port your applications. If you want, it's got full side-by-side support. You can have as many versions of .NET Core on the machine as you want, and they won't break each other. And you can now build self-contained exes. So if you want to go build a ASP.NET app or a WinForm app and make it into a single exe that does not require any .NET on the machine, you can now do that. We have awesome modern SPA web tech with Blazor and a bunch of cool language features. And so that's 3.1. Now, one final thing on this wave of stuff is, whether you're using WPF or WinForms or Blazor, we have some awesome partner companies that build awesome tools: DevExpress, Infragistics, Radzen, Grave City, Progress, Telerik, and Syncfusion. Just want to call them out, and they're also helping us on the journey to getting the third-party control support for the WinForm Designer. Now, this is where it's fun for me. We call this the journey to one.net. One of the jokes that I like to make is, when I joined Microsoft, we'd already made a lot of .NETs. There was a .NET Framework, obviously, was the first one that we shipped. And we liked it so much that we made crazy products like Windows Server.NET, which didn't contain .NET. You had to go download .NET separately, but we still called the Windows Server.NET. Then we had Compact Framework, Silverlight, there was Windows Phone, and then of course there's Mono, which is an open source version of .NET before we open sourced .NET ourselves. And then so kind of joke for me is, I'm Scott Hunter, and I work for Scott Guthrie, and Scott Hanselman works for me. So obviously, the ways to be successful at Microsoft are either to be called Scott or make a new .NET. And so, it was my team that went and created .NET Core a couple of years ago. But now that we've done that, what we'd like to do is, we were looking and thinking about, .NET Core 4.0 would be the next version, and we already have a .NET Framework 4.8. That felt kind of weird. And so what we'd like to do is basically say that moving forward, we've already taken the best of .NET Framework in 3.1 and moved it to 4. We want to take the tech from Xamarin and Mono, the best of that, and move it into .NET Core. And then we're going to rebrand the entire thing to .NET 5 because .NET 5 is bigger than .NET 4. But there's a bunch of cool things that happen along this .NET 5 and 6, what we're going to call Wave, because all the features don't fit into .NET 5. We need 2 versions of this, but one of these is a single SDK. And what I mean by single SDK is you can build any of those app types I showed before: web, cloud, mobile, desktop, IoT, ML, gaming, all with a single SDK. We're going to make this SDK super small, meaning it's only going to contain console apps and class library by default. And you'll have to actually run a command .NET install ASP.NET or .NET install desktop to add the components you want. We don't want to be a big bloated framework. It's got 1 BCL. Today, if you build a Xamarin application, you're using the Mono BCL. If you build a WinForm applications on Core, you're using the .NET Core BCL. We want to have the exact same base class libraries, the strings and dates and stuff like that. So your code is super portable across all those different platforms. We want to have a single unified toolchain. If you've tried .NET Core, it's got command line tools like .NET Run, .NET Build, .NET New. We want all the app types to work in that model. We want to have awesome cross-platform UI, and I'll talk about that a little bit later on. We want to have awesome cross-platform web UI. We already have some of that today with the Blazor WebAssembly and Blazor Server, and our traditional web APIs and user pages and NDC. We want to have awesome support for what we call cloud native. We've all heard Kubernetes or Docker, containers, all these words. What do they mean? And I'll do a demo in a little bit and show you some of that. And then, of course, we're always looking to make .NET better when it comes to the speed it runs, the size on disk, the diagnostics for you to debug and check your applications. We want to make sure it works awesome in the cloud that we build here. And I think that when we in this wave of .NET 5 and 6, we will basically be best of breed in every one of those app types I mentioned before: cloud, web, mobile, desktop, IoT, ML, and gaming. Now, what does cloud native mean? Cloud native means a lot of things to us. It means Linux. I'm on a Windows machine right now, and if I'm going to be building containers that are going to run in Linux in the cloud, I want to be able to develop on Linux. And so with Windows Subsystem for Linux, that's a feature we just shipped a new version of this. WSL2 shipped in Windows 10 2004 that just shipped a few weeks ago. You can just run Linux natively on a Windows device. And we've built the tools into our tools so you can actually F5 and control F5 from Visual Studio directly into Linux. Smaller microservices. We hear that microservices are supposed to be small, so they can be deployed faster. And so we've done a lot of work on being able to make .NET smaller from version to version, and I'll show you some of that in a demo. And then the biggest one, I think, and the coolest one here is opinionated microservices. If you want to go build, 3 back-end apps, a Redis cache, and a front end, how do you run and start all that stuff? And so we have a cool project called Project Tide that goes there. And then we're also building we want the perf in .NET to always be awesome, and so we're building a high-performance reverse proxy called YARP that actually will run a bunch of the Azure services. And that's how we're using .NET inside of Microsoft to push and test the limits of it. So I'm going to skip this slide and just jump right here, and let's go do a couple demos. I will say that some of the demos I'm going to do today are going to be based on, I'm going to play videos, and some are going to be on my local machine. When I was at the Build conference a few weeks ago, I had the luxury of having like 3 computers, and I don't want to jump between 3 computers here on a virtual conference. So let's jump out and show a few of these things. So the first one of these I want to show is I'm going to show running WSL2. So you just do this. And what I'm going to do here is do File New Project. And I'm going to select that I want an ASP.NET Core web application and click New. And I'm going to call this Web App Linux because we're going to run this on Linux. And click Create here. And I'll just do a regular web application. I could containerize this right now, but I don't want to. I'm going to wait and show that I don't even have to containerize anymore to run on Linux. So we're going to let this create here. And I will come over to the Pages folder, and let's open up index.cs.html. And I'm going to put an H2 in here, right here. And I'll just do environment.os version to show that version. And let's just run it real quick. And when I run this, what's going to happen is obviously it's going to launch the browser. And it's going to do it exactly what I'd expect. It's going to show that I'm running on build 10.0.19.041. Windows, that's the 2024 build. But I have something new here. I'm going to drop down my list here, and I have WSL2 in this list. I'll zoom in and show you this. And what I can do here is I can select that. And now just as fast, I've got to accept the search here. Just as fast as it was on running on Windows, now it's launching Kestrel. And the OS version now shows I'm running on Unix, and that's 4.19.84. I'm running Ubuntu right here. Super easy, super fast. Not only can I run native Linux on my Windows machine, I can put a breakpoint here, and we can run the debugger from Windows directly into that WSL2 environment. So there I am, the breakpoint hits, and you can see things just work. And so we're going to make it that easy to develop on Linux on your Windows machine. I'll show one more thing here. We've actually done a lot of work to make the container tools a lot better. And so I can come down here and say add Docker, and I can choose my OS. In this case, we're doing Linuxy stuff. So let's do Linux here. And I'll click OK. And what we can do is notice I have a Docker file. That's the only thing it adds to my project. I used to add a bunch of other stuff, and it's a fancy Docker file. There's the base image to run on top of. It's actually running in the background, getting things ready for me right now. So when I start, it'll be fast the first time. Notice here that I've got an SDK to do a build, and then I copy that version into my real container. And so I'm publishing to a small container that does not contain the SDK. And once again, I can come up and run this application. And now it will launch. Once again, accept the cert. There we go. And now it's running on top of Docker. It's the same Unix version there as well. I can open up my command prompt and do a docker ps-a. And now you can see that I'm running on containers. And so you can see how fluid it is for me to move between containers and WSL2 and all this stuff. So we think this is going to be awesome for developers to be able to do this easy. I'm going to show one more video, and then we'll do two demos that are on my machine. Some of these are videos as well because you have to use a crazy machine configuration for this. I'm going to show C#9 here and show one of my favorite features here. I've got an app here, and notice this app almost has no code in it. There's no main. If I wanted to, I could even nuke the using and put that right in front of my console.write line if I wanted to. Let's run it first. There you go, it runs. Now I'll go nuke that out. There we go. Move that up, system dot. And this is an intent of being able to make very easy C# programs that don't have a bunch of ceremony in them. But I can make this even cooler. Let me go over and change my CS project file, and I'll change my SDK from the regular SDK to the web SDK, which brings ASP.NET in. And what we're trying to do here is try to make it easy to build a microservice in as small number of lines as possible. So I'm going to nuke a bunch of white space here, and here is a sub 20 line .NET microservice. The notion that .NET requires you to have tons of files and tons of stuff is not true anymore. Single file here. I can run this. It'll still run. Launch my browser. There you go. We plan to take this tech even further in the long run, I hope, is make it to the point where I don't even have to have the CS project. I can actually just run the C# file. .NET run, name of the CS file, and even simplify the way that you can build apps in .NET. So always trying to make less lines of code, smaller, simpler, compared to our competitors. Now let me show you something really cool here. So I was talking about microservices. I talked about size on disk. I have single XE in my slide here. I'm going to go here, and what I do is I have two folders here. One's called single file 3.1. This is running the regular 3.1 bits, and this might be using some features you're not aware of. First off, notice I have I say publish single file true. That means we're telling the SDK to basically make a single exe that contains all the .NET Core. It does not require anything to be on the machine. It's a single exe. I tell it to be publish trimmed equals true. Tells it to basically strip out all of .NET Core that I don't need and make me the smallest thing possible. And because I'm doing a single exe, I have to tell it, it needs to know if it's Linux or Windows or Mac, and so I have to tell it that. So let's run that. And this will come through here. And this will end up with a microservice that's about 45 megish. Thinking. I might cheat while this is waiting. There it goes. This does take a little bit longer because of the linker, which is trying to throw stuff away. There we go. And if I go look in that folder now, let's go into the bin folder, release, NetCore 3.1, WinX64, publish. Here is my roughly 45 meg microservice. I still think that's not too bad. If you build some of these apps with like the Java JDK or something like that, you're going to be in a much bigger space, but we can do better. So I have another folder here, and inside of this, I'm running the exact same commands, except I'm running on .NET 5. And so let's run this again. And it's running as the exact same stuff, except we'll continue to work on the linker and making this tech better as we move forward. Notice it's telling me that it could change the behavior of the app. The linker, by throwing stuff away, if it throws too much away, your app could break. And we have ways to fix that, but you should be aware of that. If I go back down and look at my folder here, let's go into the bin folder, release, WinX64. Let's go into the publish folder. Now look at this. This is now 17 megs. So we went from 45 megs to 17 megs. That's a huge savings. And I always like to prove that it's real. Let's go into the publish folder here. There is that 17 meg exe. And if I run it, it should come up. I launch the browser. There the app is running. And so that's showing you that we are going to continue to make investments to make the size of these apps on disk smaller and smaller. We want to apply this as well to desktop apps, so you can make really small desktop apps that don't have any .NET on the machine. As I said, this exe, I could copy it on a memory stick to any machine. It would just run. And so that shows you the investment we're trying to make in single file. Now, let me close a couple of these things out here. Don't need that. Let's talk about Project Tie. This is one of my favorite pieces of the tech we're doing when it comes to microservices. I'm going to go back to my terminal, and I've got an app here. Let's just do a dir. You see I've got a backend folder and I got a front end folder. And I'll launch this up in VS Code. There we go. And for this application, let's say I just wanted to run it. There's a bunch of challenges running .NET applications that have a lot of different projects inside of them. In Visual Studio, there's a mechanism where you can launch more than one project at the same time. You kind of right-click on your solution and say launch multiple projects. There's a bunch of problems that come with that. And I'll explain some of those in just a second. So if I wanted to run this app today, what I have to do is go over here. I'm in the front end folder and I can do a .NET run. We'll give this a chance to boot up here. There we go. And I'll launch the app in the browser here. And of course, this isn't going to run. And it's because I forgot to start the back end. I need to remember to run both projects, which is actually kind of hard to do from VS Code. You have to build a special command that launches both of the projects yourself. Now I've got the back end running. The app kind of hooks up, but we can do better than this. So let's close it. And I'm going to close this folder out. Let's close this folder out. And what we've created is something called tie. And the idea of tie is it lets you tie projects together. And so I can do tie run at the top of my folder here. And what it's going to do is it's going to go scan all the folders and find all the CS projects, and it's going to run them. And it's going to give me more than that. When I ran those other projects before, there's a whole bunch of things I could not have done. So let's go here and launch this up. And now when I run multiple projects, I'm getting a dashboard. The dashboard tells me, hey, I found 2 projects. I found a front-end project and a back-end project. They're projects, meaning they're CS projects, and it gives me a path to the CS project. For each of those projects, I can now see the URLs for the projects and just click them to open the browser. I can go look at the logs for each of these projects running here and here. I can even go over here, and if I click on this, I can go see some of the performance counters for that particular project. This is stuff that you never would have seen before, just running things from the command line. Now, this is still not going to work, and that's because my app's not set up correctly. And if I click this, I'm going to get a failure that it can't find the back end because it doesn't know what the port is. There we go. No connection could be made because the target machine actively refused it. So let's close that out, and I'm going to stop tie for a second. I'm stopping and starting tie. The latest release of tie that just came out this week, I believe, does support tie run watch, where you can start it, and then as you change your source code files, it'll reboot that part for you automatically without having to go back and start and stop. But let's go in here. And this is my front-end project. And notice that today, it actually hard codes the URL for the backend. We do have a file, launch settings.json, that you can actually have in your applications to configure these types of things. But even then, making all those ports match and stuff, if you get to put that in source control, it's just not good. We can do better. So let me tieify this project. So I'm going to go in here. This is my CS project file, and I'm going to actually uncomment a package. This is something that would be just built into .NET in the future. And this is a configuration extension. So yeah, sure, restore that for me. And what that lets me do is I can go to my startup file here, and now instead of having this hard-coded URL, I can just say base address equals configuration get service URI backend. You saw before those things were called backend and front end. What tie will do for me is when it boots these things up, it actually will inject an environment variable into each of those processes with the actual correct port numbers. And so I can just tell my app, use the back end, use the front end, and all that port mapping is done automatically. This is super important when you get to something like Kubernetes or Docker, where those ports change based on the environment you're running in. Now with tie, because we're flowing that configuration information directly into the processes, you don't have to worry about that. So if I save this and I come back over here and I do a tie run again, now everything's going to work. Let's go here, let it run. There we go. And I can just go back to my dashboard. I can refresh the dashboard. There's my application. Click the URI. Everything just works. Now this is great. But we can do so much more again. So I'm going to close out that window. Stop this one more time. And what I'm going to do is go back to my prompt here, and I'm going to type tie init. So before I mentioned that when I ran tie run, it went and figured out what CS project files were there. Maybe I want that to be the actual configuration that I can change. So by typing tie init, oops, it's going to go and create a file for me. Let's go back to my VS Code. And here's the Thai YAML file. And notice it basically does all the things that it was self-discovering for me is now in textual format. You can see that I've got, we're calling it microservice. It's got a front end with a CS proj, a back end with a CS proj. And what's cool here is I can come to my notepad here, and I'm going to add a little bit of goop. I'm going to go and just stick this over here. And what I just did is I added 2 more services inside of my Thai YAML file. The first one is, it's got a name called Redis. And notice instead of being a project, this is now an image. And what that means is, that means container image. And so what it's going to go do for that is it's going to go pull a container out of the container registry and put it on my machine. And it's basically going to run Redis. So without installing Redis on my machine, I now have Redis in this project. In fact, I run Redis twice. Once to run as itself, and then once again to run it as a monitor. And so my application is now Dockerified. It can run, I can put SQL Server in this way. I could put Postgres in this way. There's tons of things I could put in this way. Now that I've done that, let's go use the Redis cache before I boot it up. So I'm going to go back into the CS proj here. And I'm going to comment out one more thing. Let's comment this out. This is the package reference to the Microsoft Exchange caching, the Stack Exchange Redis. And this is important. I need this because I'm going to go to my startup CS, and I'm going to add Docker support. So this says add Stack Exchange Redis cache. And then it says basically I need to configure this. So I'm going to basically inject the Redis cache into the DI on the machine. And notice once again, I didn't put ports in here. I basically just said get connection string Redis, because once again, we're going to do all that stuff for you, and the right ports will just show up there, and I don't have to worry about that as things change. And then let's go to my index.cshtml, and I have a tag helper in here, and one that we built. Distributed cache, I give my cache a name weather, and then I say, after 5 seconds, I want the cache to expire. It's going to squiggle because I need to come down here and uncomment the closing of the tag. Save that. So now we've added Redis cache to our application. I didn't write any Docker files. I don't know how to write Docker files. I added a package to enable the Redis cache support in .NET Core. I wrap my code in a tag helper that does caching for me automatically. And now, if I go back to my command prompt and I run Thai run again, the output's going to be a little different because a lot more stuff's going to happen here. So now I can see running Docker command, running image Redis, running image. There's a whole bunch of stuff going on here. Wow, it's kind of interesting. Let's go back to my dashboard. Let's do a refresh here. And now I've got 4 projects, and 2 of them are containers. And the cool thing here, as I said, I didn't write Docker files. I didn't write home charts or any of that kind of stuff. I just said I want an image, gave it a port. It's ready to go. I can go back to my front-end application. And if I start refreshing the screen, nothing changes. It just changed. It's been 5 seconds. Just changed again. It's been 5 seconds. So you can see that it actually is caching. That cache work is working here, just like I wanted. I can come back over here. Let's go look at the logs. And you can see all the cache hits that are happening here. It was glitchy for some reason. I don't know why it was not cooperating. Cache was working, and I was not seeing the logs. Weirdo. But still not good enough. Let me close the app out again, and I want to show one final thing. Now I've built an application. It's got 2 apps that are running normally on my machine. I've got 2 apps that are running in containers. if I'm going to really run this in Kubernetes or in the cloud and as containers, everything's going to run as a container. If I do try run -- help, notice that there is a -- docker command I can run. And so if I do that, and say -- docker, now all of my apps are going to run inside of containers. And so this puts me in the state I want to be in to actually publish this up to something like Azure Kubernetes Service, because all the pieces are going to run in containers in that world. And so before I get ready to publish and do that, I can test it right here. If I go back to my CS project file again, or back to my dashboard again, and I refresh, now notice everything is turned into a container. Just that easy. If I click the link over here, works just like it did before. Now I'm running in containers using Docker. And so it's just amazing how easy this stuff is now. Why this was important is because the next step I could do is, what if I wanted to publish this to the cloud? What is my step to do? Well, my step to do is to go back to my VS Code, and I will go back to that .yaml file, and all I'm going to do is grab this right here, and before I get to services, I'm going to basically say registry build 2020 tie.azure.cr.io. I'm giving it basically a container registry that I have and I own. And then I can go back to my command prompt and I just type tie. Notice I have a command here called deploy. And so literally I could just do tie deploy, and this application will publish up to the Azure Container Registry and be there. And if I have triggers set up in like Kubernetes, it'll notice I put new images in, it'll pull them, and then because of all that port mapping magic I showed you before, you don't have to worry about all the networking challenges between all these different applications running in Kubernetes. And I'm showing all this in the context of VS Code and command prompt, but we're going to make this go through Visual Studio as well. You're going to have an awesome experience to run multi-app .NET applications in VS or VS Code. And as I said, this tech's already better. I'm not running it because I'm not going to change my machine the day of running something, but I could have done something like this, and it would have watched my code changes and just restarted automatically for me and give you that great inner loop you expect in .NET. So this is tie, and I think it's one of the most exciting things that we're doing. And so that's that. So let's get back here and let's talk about cross-platform native UI. This is a thing people have been asking us for years, and so let's talk about that. So I want to introduce what we're going to call .NET Multi-Platform App UI. And this will make sense. It's called Multi-Platform App UI because you can have a single project that can run on iOS, Android, Windows, and Mac, maybe in the future on Linux as well. But you can see basically this is .NET MAUI. That's the abbreviation of .NET Multi-Platform App UI, and it runs on .NET. And it has a couple of things that it cares about. One is cross-platform native UI. We want to do that. The new thing, if you're a Xamarin developer today, you might have seen that a Xamarin project will typically have an Android project, it'll have an iOS project, it'll have a Windows project, potentially. It'll have a shared class library, a lot of moving parts. We just want to have that be a single project. And from that, just right-click and deploy to what you want. So deploy to multiple devices, mobile and desktop. Just right-click on the project and say, run it on my iPhone or run it on my Windows device. Make that really easy. This is an evolution of Xamarin Forms. We're really taking the Xamarin tech, and as we unify .NET into what we call one .NET, it's just part of the stack. And it's going to target .NET 6, but we'll have previews later this year. Around the RC time of .NET 5, we'll have previews of this available on GitHub that you can try. And you can look today in github.com/.net/MAUI. There's stuff there today about how we build this. What does it look like from the code? Notice that before we would have had Xamarin.Forms, that's now System.UI. We used to have Xamarin.Essentials, that's now System.Devices. You can tell it these texts that used to feel like they might have been outside of .NET are now in .NET. File new is the multi-platform app UI, .NET. And then for the first time ever, you've got a CLI, .NET New MAUI. What do we do for the rest of the Xamarin project? We're going to rebrand the projects, so it's just .NET for iOS, .NET for Android, The namespaces stay the same, but you'll also notice they're all using the new SDK style that we have in the .NET Core projects. And you have .NET New iOS and .NET New Android. So we think this unifies the Xamarin technology directly into .NET, and I'm super excited about it. And so let's do a quick demo of Maui. So I'll go back here. And we'll first run it on a Mac and show a couple things that you never could have done before. So here I am on my Mac. I'm going to make a folder called Maui. And I'll jump into that folder. And for the first time ever, I can do a .NET New Maui. You've never been able to build a Xamarin app from the command line. Now you can. And I'll do an LS here to show you there's the iOS, Android. We don't have the single project working on this build yet. But let me go into do a quick restore. And then we'll launch VS Code after doing the restore. And I'll show you some of the new tech that we have in Maui. So let's do a code dot. And here's my project. I'm going to drill into the Maui folder here. Let's go to the main page.cs. And first thing you might notice here is there's no XAML here. This is actually written in C#. So we are going to give you an MVU C# model to build your UI in native C# if you want. Let me show you something else new. Right from VS Code, I can launch the iOS emulator here. Pop it up here. App is building. And I'm going to show you some features called hot reload and hot restart. They're pretty amazing. So this app's going to come up on my phone here. There it is, installed. And let's click that. And when the app launches, just click the plus button. You can see the value increment. Now I want to change the code. That label should not actually be stuck over there where it is. So you look at the code here. I'm going to go fix that text alignment. I'm going to just type .center here. Now I'm not going to rebuild or do anything. I didn't even save. I just did center and it moved to the center. So we're making the inner loop really fast. Make the color pink. Boom, it's pink. I'm not a big fan of pink myself, so I'm going to go back to black. Back to black. If I want, let's go change some of that source code. I'm going to change the plus plus to a minus minus. Like that. And I'll just press the plus button down there. It never goes backwards. I need to fix that plus button too. Let's go over here and change the code here. Now the label changes. And so what you can see is how easy it is to build an application in .NET with Maui with this new MVU pattern. Write all your UI in C# if you want. So let me make this go away. We'll do one more Maui demo here. This is Maui running on Windows. And you see me here. There's that new template. I'm not going to create that. I'm just going to close this out. And I'm going to open another VS that has a Maui project inside it, a .NET Maui project. And this time I want to show, even though I showed you that brand new C#, you don't have to use that new C#. The Xamarin customers are very used to a XAML. We have the same XAML support we've always had here. And so you can see I've got my stack layout. I've got my XAML bindings here. And so we're going to make it super easy for you to move from Xamarin to .NET Maui, staying in XAML if you want to. Of course, you can also write UI in that new C#. But let's show something else here. I'm just going to run this on Windows. I want this inner loop to be super fast. I don't want to run an emulator or anything like that. If I'm on a Mac, I want to run it on the Mac. If I'm on the Windows, I just want to run it on Windows. You can see the diagnostic tools boot up. Here the app is running. Boom. And so once again, we want to make the default for building these apps super, super fast. And so you can run the app natively on the device you're designing it on without having to worry about using an emulator. Now, I mentioned before we added a feature called hot reload and hot restart. It's already in Visual Studio today for Xamarin projects. And what it does is it allows me to just basically plug my iPhone into my PC and just have it work. I didn't have to install any weird stuff. I don't even have to have anything more than a free Apple developer kit account. I can get it developer.apple.com. I plug my phone in, It's going to show up here in the list as Scott's iPhone. I will click that. And this tech, as I said, is super amazing. I've got a copy of, let's deploy it to the iPhone. I've got a copy of Reflector running down here. That's an app that actually will mirror my iPhone on the PC. And here it is. And I can run the app on my phone. Now, I also want to call out that as I'm doing this, I don't have to have a Mac anywhere in the system. For development, I can actually do it just with a Windows machine and a free Apple developer account, and it just works without installing anything on my device at all. Just plug the device in and it goes. And I think that's super exciting. You do have to have a Mac to deploy to the actual application store, but if you have a team of 20, you only need one Mac. Now this is what's really cool. This is a single project. Notice this. It's if you're used to Xamarin, you would have had a couple of projects here. Now I've locked this down to a single project. It's got a resource node. Obviously, I need a place to share my icons. There's my favorite .NET bot icon, and that I can now share that across Windows, Mac, iOS, and Android. I can also put things like fonts in here. Because I want to have my own fonts for my apps that look good on my devices. So there's a couple of my fonts. Now I do want to say the coolest, I think, node in this project is the platform node. And so if I scroll up here and drop this down, you're going to see basically I've got a folder for Android, iOS, and Windows. And that's where I would write code that only runs on those platforms. So once again, the Bluetooth adapter is code that is hard-coded to the actual APIs on the individual platforms. So once again, we give you this single project that runs all your applications. You can run with no emulator. You can easily plug your devices in and have them work. And that's .NET MAUI. And I think that's super exciting stuff. I'm going to do one more MAUI demo here real quick. And this is a crazy demo of where we think things could be going in the future. So let me do this. And this is a MAUI app, .NET MAUI app. I'm going to run it on my device here. And what's going to happen when I do that is it'll open here. There it is. And this is a native app, native UI. So cool. Push the button, does the thing. Native controls. Deploy all your devices. Now, how can I make this cooler? There's this notion of apps that people build today where they're called hybrid, and that's a mix of web tech and a mix of native tech. A lot of folks use things like React Native for that kind of stuff. But what I've got here is I'm going to basically nuke some stuff here, and now I'm going to actually take my native app and I'm going to put a Blazor web view inside of it, and run this. And then here is the app again, and now that's my web code and my native controls all in the same app. Things still work, and you might be going, Scott, this is not really true. This is you're faking this. This is actually Blazor, which means I can write C# inside of here. Do this. Write a for loop here. Need to put a p tag here, and display that number there, and run this one more time. Now you can see that not only is that web actually is running my C#. You can see the markup there, just like you would expect. But I can make it even cooler. Let me just make that, and I'll comment this out. And let's go to a slightly different version of this. I've got another one here. And in this case, this is a Blazor web view, but it's going to actually talk to the same state the native controls are talking to. Up here, notice when I click the button, we called counterstate.increment. And when I displayed the number, it was counterstate.currentCount. You can see I injected the counter state into this page. In this case, my Blazor tech is calling the exact same counterstate.current, and the exact same counterstate.increment count. If I run this application now, what's going to happen? It's complaining that I never closed the other app. Be kind, close the app, Scott. There we go. And so now I have a mix of native tech, web tech in the same app. I press increment, they both change because we're sharing state across the boundaries. Share the state across the two boundaries. I can go all the way. So let's type that out. And now what I'm basically doing here is I'm putting a web view in saying, show me my entire web UI for my Blazor app. So I've got my native UI up here at the top, and I have a full Blazor application running in the bottom. And I'll tell you why this is important in just a second. So here we are. Now you see the full Blazor app running here. I've got my native stuff at the top here. It's got the fetch data you would expect. All this tech running together in the same application. Notice the counters are still hooked up. We're sharing state across the native boundary and the web boundary. And so you might ask, why, Scott? What's the point of this tech? This is us taking a look at, you're all familiar with Electron apps. That's where you take a native shell and you actually run some web technology inside of it. This is doing the same thing with .NET. I took Maui, .NET Maui, and used it as my native shell. And inside of it, I can host a web view where I can run a Blazor application. Because this is a native application, it means that Blazor app now has access to the actual operating system, like an Electron app can. So it can open a file. It could do all the things you would expect a desktop-style application to do. So this is an experiment at this point, but it is something I think as we get towards the end of the .NET 5 wave, you'll see us take this experiment a step further and turn it into reality. So let me close this out. And so super excited about all the .NET Maui stuff and what we can, how far we can take it. So where we kind of are today, we have previews of .NET 5 out. Once again, .NET is completely side by side, which means you can install .NET 5 on a machine with .NET Core 3.1 on it. Won't break anything, you should be good. You can start checking out these cloud native improvements that I talked about, single file. You can go grab a preview of Project Thai to go try that cool way of building applications. And as I said, in just a few months, when the first .NET 6 branch is open, you'll be able to grab .NET Maui in preview and try that out. We just shipped preview 5 this week of .NET 5. You can try that out now. And a lot of folks ask me, what about UWP? UWP stands for Universal Windows Programs, and it was a model that was shipped a couple of years ago. People have always asked, Scott, when is UWP coming to Core? And the answer is it's not going to come to Core, and that's because the Windows team has announced WinUI 3. It's the evolution of UWP. It basically gives you the ability to build awesome Windows 10 desktop applications, taking advantage of all the touch features, all that kind of stuff, all the stuff you got UWP, but it's different. It doesn't require a sandbox to run in. It doesn't require the App Store. You can actually just copy one of these applications to a machine, and all the features work on all versions of Windows 10. It supports .NET 5 and C++, and you can grab it today and try it at aka.ms/winui, and we'll continue to make that work better and better as we go forward. The next thing I want to talk about is the schedules. You might ask, why did I call this the .NET 5/.NET 6 wave? I did that because you now ship .NET every year. We want to be very consistent to our developers. We want you to know when the next version is coming. We want you to know how long the support is, and never be guessed by going, oh, you shipped it in March this year, and June this year, and November this year. We want to have a clear cadence. We actually got this idea from other open source projects like Ubuntu and Node.js that do the same thing, predictable. So .NET 5 will ship this November, and you can see there's a major release every single year, and every other year is a long-term support. So if you want to stay on 3.1, you can stay on it technically until November of 2022. And then at that point, you would want to move to .NET 6, and you could stay on it until November of 2024. So you have roughly 3+ years of that support cycle. But the point here is we want to be very predictable, very easy for you to know what's coming. It also helps things like Azure and Amazon and other cloud services to know what our schedule is and have these runtimes available for you in those things. And then I want to talk about .NET Conf as well. This is our virtual conference where we launch the next versions of our products. And so this year, kind of giving away the .NET 5 release date, it's going to be November 10th, because that's the day that .NET Conf starts. That'll be the launch of .NET 5. It's a 3-day virtual event. It's half done by people on my team at Microsoft, and it's half done by the community. So it's kind of a thing. And save the date, put on your calendars. www.netconf.net is open today for you to go check things out. And with that, I'll do one more quick demo because I got 5 minutes left. Use all the time we have. And I'll do this one on my machine. So let me do this. I'm going to go and open a VS here. And let's open up this one. I want to show the model builder that we have for doing AI real quick. If I can do it in 4 minutes. So what I can do is I can take a .NET project, and I'm not going to run it because I don't have time. And if I want to add AI to it, I can just say, add machine learning. And then we give you a bunch of choices of machine learning topics. In this case, for this app, I want to do image classification. So I'm going to select image classification. Like that. And it needs data. You have to train the model. So I'm going to go click here. And I have ML.NET here and card image train. And that's good. And so for image classification, that's when you ask it to say, what is this image? Is it a broken car? Is it a good looking car? What is it? I've got 2 folders here, damaged and not damaged, each with 920 images in it. Then what I do is I go and say train. And I can actually train locally on my machine or train in the cloud. I've actually done this already. Close out of this VS. I'm going to go to the one that I've trained already. You see it's got a 91% accuracy. And what I'll do is I'll do evaluate. At this point, if I wanted to, I could test that model. I could drag a picture of a wrecked car or a not wrecked car over here, and it would tell me if it thought they were wrecked or not. But where it gets cool is I can say add projects. And so when I do that, now I have a console project that showed up, and I have a model project that showed up in my Visual Studio over here. And then it gave me some code that's required to go and hook that up so it works. In this case, I've actually got my app ready to go. I'm just going to go up here. I can do this in 2 minutes. Uncomment out the model. To actually detect if the car is wrecked or not, all I do is I basically say model.predict. I give it the file path of the image of the car that I've taken, picture of the car I've taken, and then it returns a result. And all I got to do here is say, give me the prediction is damaged, and give me the score. So let's save that. Let's run the app. This is a Blazor application that you could use at a car rental facility when a car comes in to be checked in. Let's get this up and running. I need the dashboard. And I'll sign in real quick. In the app. And now I check a car in. I'm going to check in 102. Here we go. And in my case, look here, door's in bad shape. Got this ugly picture. My ML model, I can now click detect. So I can just take a picture of the car with my phone. Oh no, I crashed. Tried to rush too fast. But what that model would typically do is actually go and make that call dynamically for me. and tell me if that's good or bad, and I would be good to go. But I'm almost out of time, so I'm going to stop and not debug it here on the stage. With that said, .NET Core 3.1 LTS is available today. It is all new .NET projects should be built on this. It's got all the new features. It's ready for full production. Think about that. At the same time, if you want to try the .NET 5 stuff we've been working on, try that and give us some feedback. You can grab that today. And with that said, I just want to say thank you for having me at NDC Oslo this year. I wish I could be there in person, but I definitely hope to see if I can come back next year and be there in person. Thank you folks very much.
Good morning. Hello, my dear friends. Well, you're close enough to be called friends. We're about as far away from each other as everyone else is at the moment. Welcome to this talk on the final day of NDC. If you're still in bed and if you're still watching from bed, I hope you're very comfortable. And even if you're not, I still hope that you are as comfortable as you can be on this beautiful morning. At least here in Oslo, the weather is stellar and it's a lovely day. So let's make it just as lovely in here. This talk is about getting your feet wet with open source, about getting started, and the intended audience is people who are quite new to open source at all. That means that if you're a veteran contributor, if you've been around the block 2, 3, 4, 5 times, you might not have a lot to learn right here. However, please do stick around because you might pick up a thing or two, and if nothing else, maybe you can teach me something. During the talk, I cannot see anyone. All I've got is my feed and my face and my slides. So that means if you've got a question or anything, because I don't have a chat, ask it in the Slack for conference room 1, and I will try to get to it at the end of the presentation. So how about we actually get started? Let's start by why am I telling you about this and who am I? My name is Thomas Hartman, and these are all my socials. If you want to get in touch with me, reach me here. There is nothing else on this slide, and that is because there's nothing notable to put here. I am very ordinary, to put it that way. Just a year ago, I graduated at university and got properly into programming. I had never done any of it before starting university. So that means I'm still very, very new. And that is exactly why I am speaking about this, because I haven't been around for ages. I still remember what it's like to be new. I am still new. I still struggle with all these things that I'm going to talk about. And so it's easier to teach yourself what you didn't know 5 minutes ago than it is to teach yourself what you didn't know 5 years ago, because your frame of reference is so different. And so that's why I'm talking about this. As I mentioned, here are my socials. If you can't reach me on Slack, because from what I hear, the Slack team will be shut down after the conference, do try and reach me on Twitter or anywhere else. And if you want to read some stuff about tech, I've got a blog too, so as everyone else does, right? But let's actually get started with this. And if we're going to talk about open source and contributing, we've got to first talk about what it is and get some sort of definition on the go. But that might not be super easy because it's open source. It means it's not actually governed by any real body. However, the Open Source Initiative, or the OSI for short, have a definition that's generally regarded as the de facto definition. The OSI is an organization, a non-profit organization that have for over 20 years been working to raise awareness and adoption of open source software. And they are also behind the URL opensource.org. Now, their definition says that open source doesn't just mean access to the source code. The distribution terms of open source must comply with a set of criteria. Now, this set of criteria is fairly long, not very long, it's about 10 or so bullet points. But in our case, and for this talk, it's much too stringent because all that we care about in this talk are 2 things. Number 1, the source code must be available somewhere online. And number 2, the maintainers, the people who work with the source code, must accept contributions. That is a definition we will be using when talking about open source here. That's not to say that talking about licenses, about software freedoms, about open source versus free software and the like are unimportant topics. They are very important and very interesting if that's your cup of tea. But for the purposes of this talk, it would only serve to muddy the waters. So for that sake, we're making it easier and using a much simpler definition. I mentioned that for something to count as open source software, in our case, it needs to be accessible, and it needs to have a project where a maintainer is willing to accept contributions. This is usually done via various source forges. GitHub is probably the most well-known one, but you've also got things like GitLab, like Bitbucket, like SourceHut, and others. And these are known as source forges. These are places where code lives and where you can interact with both the code and with people who make the code. They usually have some sort of issue tracker, a ticketing system, if you will, where you can report bugs, where you can request features, and where you can interact with the people who make the software and talk about it. These projects are maintained by people who are called maintainers, obviously. The other thing about this talk that we want to talk about is contributions and contributing. So what is a contribution? Now that we know that open source software, in our terms, is software that's somewhere online and that you can contribute to, what is a contribution? The most obvious answer, perhaps, is code itself. It is, after all, the building block of software. It is code. So it's a simple but very correct answer. Code is contribution. However, it is not the only form of contribution. Documentation is another form, and documentation is at least as important as code. The thing about documentation is it's usually the last thing to get done because it's what people really don't want to do. Because after you spend days or weeks trying to come up with this perfect algorithm and you create the project and everything lives up here and you know exactly how it works, you don't really want to sit down and try and spell it out for someone because it takes time. But it is very necessary because the only way you can share this with other people and make other people understand it is by writing it down. So if you contribute documentation, that is not only helpful to you because you need to understand enough about the project to actually write about it and write about it in a sensible and coherent fashion, but you also help the project itself because they now get more documentation, and that helps newcomers to the project, be they end users or other developers. So documentation is this triple whammy. It's a great place to get started too because it means you get to learn and you also have a fresh set of eyes, which is really important. Also, by contributing documentation, you have to get it run by an expert. The expert in this case being the maintainer. And that means they will check your work and make sure that it's actually correct and accurate. Obviously, there are also other forms of contributions, such as marketing, design, and other whatever you want to. However, this talk will focus mainly on code and on documentation, mostly because those are the areas where I have experience. Now, I mentioned that these forges have ticketing system, issue trackers. Does opening an issue count as a contribution? It's a valid question, and it can be hard to answer. My stance on this is that it depends on the issue, but if it's a well-written issue, then yes, it definitely counts as a contribution because it helps the maintainers to see to find faults with the program, to figure out what doesn't work or what users want. It helps them improve things by getting real feedback from real users. So, assuming that it's a well-written issue, yes, I would say it counts as a contribution. But do be mindful about just opening issues willy-nilly because they do take time to triage and someone has to look at them. If they're duplicates of issues that are already there, then it just creates extra work, which is also not ideal. So with our definition of open source, of contributions and having talked about issues, let's get started. Let's actually look at 4 simple steps to get you started in open source. This will be a fairly high-level overview, and I won't dig really deep into any technical topics, but it's worth catching because it's 4 steps that you can always follow. We'll start with number 1. Identify a problem. If you're going to contribute something, you need something to contribute to. You need something to fix, something to do, and that is the problem. So what is a good problem? Well, that is up to you. It can be a number of things. For instance, if you want to learn a new language, maybe you find a project that's written in the language you want to learn, you sit down and you find an issue that looks easy enough to solve. Or maybe you just want to get started with learning about a framework. Say, take the JavaScript framework React, for instance. If you want to learn how it's structured, how it actually works, a great way to really dig into the code base is to find an issue. A lot of projects will have labels for their issues that are equivalent of good first issue, or the like issues that are intended or requested, where the maintainers request someone who's new to the project to get started. These will usually be fairly simple, and the maintainers will also be happy to help you get along to get started. These issues are labeled as such to indicate that it's a good place to get started with a project. So this is a great way to get started. Another form, or another way to find the problem is, again, documentation. Say you're learning a new framework, or you're working through a new project for whatever reason, and you're following along to the documentation, and suddenly you get stuck. You get stuck and you spend hours searching for a solution and trying and wrecking your head trying to figure out what's wrong, and maybe something's missing, or maybe it's just plain wrong. This is a great time for you to step up and go, hey, this is incorrect. I want to fix this. In fact, that is how I got my very first contribution. I'd barely gotten started programming, and I was working on a project, and I wanted to check out a tag with Git. Now, if you don't know what this is, doesn't really matter. Just, if you're new to Git, it's maybe not the standard way of working, but the documentation said you can't do that. Git can't check out tags. But I was confused, because the documentation said you can't do it in plain words, yet on my machine, it worked perfectly. I checked out a tag and things were all right. So I thought, this seems strange. I'll ask about it. And so I opened an issue, and sure enough, the documentation was out of date. This was added at a later time and at a later version of the software. So I ended up writing a section about it, about checking out tags. And that also led me into reading more about Git, and I had to research headless mode, or a headless state, because if you check out a tag, you might be left in a headless state. And this is about as scary as it sounds. And definitely, at least if you're new to Git or version control software like it, you can be really scared that you're going to mess something up. But I had to learn what it is and how you get out of it, and write a little section on that too. Really helpful, both for me and for the documentation. Now, if you ask me today, can I explain to you exactly what it is and how you get out of it? Maybe, but don't really count on it. Yeah, these things slip, but yeah, that happens. But on the topic of documentation, there's a quote by Chris Coyier, a quite prominent figure in the front-end world and also the editor of CSS Tricks. And he says, write the blog post you wish you'd found when you searched for it. And for documentation, it's the same thing. If the documentation that you find isn't up to par, if it isn't what you wish you'd found, if it's got wrong steps, or if it's written in a roundabout way and it's hard to understand, fix it. Write what you wish you'd found. go change it and make it better. Plus, again, if you're new to the project, that's a bonus point, because in your eyes, you don't have the same frame of reference that the maintainers have. You don't know everything about the project in the way that they do. So you know exactly what it's like to learn 5 minutes ago, whereas they can't remember what it was like to learn 5 years ago, or 5 months, or however long they've been on the project. So that means contributing documentation as a new person, as a new developer, as a new contributor to the project. Super helpful. But these are a couple of ways, but my favorite way of identifying a problem is do something that makes life easier for you. If you've ever been in a situation where you think, oh, I just wish that this little piece of software did this little thing different, or could do this, then you know what I'm talking about. Solving a problem that makes life easier for you has one really important advantage to just picking an issue at random from an issue tracker. And that is, it offers intrinsic motivation. It means you want to solve it because you keep running into it over and over and over again, most likely. Or it's something that you really think is important or that you are passionate about. And that's really what you need to get yourself through. I heard a term recently about the GitHub graveyard, and I'm sure we're all guilty of this. I can't see any of you, but I'm sure all of you would raise your hands if I were to ask how many of you have more than 5 abandoned projects lying around somewhere. I know I've got loads. Because you get started and it's, oh yeah, this is so cool. And you just never have the motivation to get across like the 70% mark. You don't have what it takes to get those last percentages done, because once you've done the proof of concept, it's like, oh, this works. You're done. There's nothing motivating you to keep going. But if it's something that will actually help you out, then you keep pushing. Then you want it to get done because it'll make life easier. It might be a small quality of life adjustment, but it's really important. It will take time, but it will be so worth it in the end. Now, I'm sure most of you are familiar with Harry Potter. And if you're not, it's a series of books about a magical world where witches and wizards live and magic is real. They use wands. The important thing is, it's not the wizard or the witch that chooses the wand, but it's the wand that chooses the witch or the wizard. And in a similar way, in open source, I don't think that it's the best for the developer to pick an issue, but rather it's the issue that picks the developer. It's the issue that finds someone who's caring enough and who's actually annoyed enough at this issue to fix it. And that is a great way to get started. And this is also how I came into, or how I got my last contribution, or my most significant one to date. Because I was playing with new shell, which is a new shell, as the name implies. And it is written in Rust, which is also great, because sometimes your other interests coincide with the issues you find. And I've been really into Rust for a long time. And so getting, hey, it's a shell, it's written in Rust, awesome. It's 2 things that I love right there. And I was using it with Kubernetes, another thing that I think is really cool. And what happened was that I got some output that was nice and human readable. I thought, oh, this would be so great. And it looks like a table, so new shell should be able to parse this and create a really good data structure, because that's what new shell does. It gives you a table structure for all your things. Look it up, super cool. But the problem is the output that I got from this command, he wasn't in any standard machine readable format. It was very human readable, but not machine readable. So what do? I open an issue, say, hey, here's my use case. I wish this would work. It doesn't. Can we fix it, or is there another way to get around it? Again, I was told, oh, we should do this. This sounds like a reasonable thing for us to do. And so I wrote a parser for space-separated values, like tables, natural tables that are just formatted with spaces. It's great. 3 things that I love, smooshed together into one, makes for intrinsic motivation, makes for something you want to do. Now, it turns out in the end that, sure, I could have probably just gotten the JSON output and piped it through some sort of parser, but where's the fun in that, right? Okay, so assuming you've identified a problem, you know what you want to work on now, you know you've found the project, you found the problem you want to solve. What's the next step? Open an issue. Or rather, talk to the powers that be, talk to the maintainers. You start by navigating to the project. At this point, you might want to look in the project repo. In the root folder, there might be something called a contributing file, usually called contributing in all caps. This file might, if it exists, might contain information on where and how you open issues. You should probably have a look at this before you go any further, but more than likely, it's okay to just jump directly to the issue tracker and look for similar issues. If you found an issue, then you're probably not the first one to find it. So instead of creating more work and duplicate work for the maintainers, let's try and see if we can find the issue already. Has it been opened? If you find an issue that reports the same thing that you want to say, whether it's the same feature, the same bug, the same missing documentation, check it. Do the maintainers agree that this should be fixed, that is an issue? And if they do, is anyone else working on it? Here's the thing, in open source, when it's free for everyone to work on, you still want some sort of structure. If someone has already started working on an issue, you don't really want to come in and just steal it. That would be a breach of etiquette because they're already working on it. They've claimed it, so to speak. And I'm sure you can identify with that. If you're working on something and you really want to do this and you want to show that, hey, I can do this, and then someone else comes and steals it in front of your nose, that's generally not a good feeling. So see if anyone has claimed it. If they haven't, say, I want to do it. If they have and nothing's happened for a long time, it's okay to poke them and go, hey, are you still working on this, or what's the status? So that's one way to get going. The other, if the issue doesn't exist already, create a new issue. Explain what your problem is. Explain whether it's a feature request, whether it's a bug report, or whether it's documentation, or whatever you want to do. Explain why, and explain how. Explain also that you'd be happy to take this on and do this. But remember, especially if it's a feature, it might not be that it aligns with the project's goals. And in the end, it is the maintainers that own the project. It is the maintainers that decide whether something gets merged in or not. As such, it is important to open an issue before you start working on the problem so that you don't just show up with a bunch of code and go, hey, here's my stuff, because maybe you don't want it. Usually though, or often, depending on what your feature is, the maintainers might be happy to go along with it, and it's a good thing to do, and you can get started. If you can't, and if they don't want this issue, you can either go back and identify another problem, or you could create a fork and do stuff on your own, but that's not what we're going to talk about now. We're going to assume that you got the issue, that you claimed what you wanted, or that you created a new one, and that is yours to work on. And so that's step 2. Step number 3, do the work. Just do it. It's that simple. This you might expect to be the meat of the talk, but I can't really say much here because what you do and how you work on it really depends on what the issue is and how you want to fix it. This is your time to shine. This is where you step forward and go, okay, I want to fix this and I want to fix that, and so and so. But remember the contributing file I mentioned? Use that before you start and see if they have certain guidelines like code style and like commit style and the like. Try and follow this as much as you can. Write tests if they require that. Do continuous integration, work on various things. Just try and follow this and talk to the maintainers if something's unclear. And do feel free to ask them questions while you're working. But aside from that, I don't have any secret tips or tricks for this. All you got to do is just grind through it. Sit down, do the work, and make it shine. Now, whether this is fun or not, that depends on you. That depends on how you feel about the issue. But more than likely, as a developer, I'd sure hope that you want to do this because you're doing this in your spare time, presumably, and for no pay. So hopefully you're into it. Right, so that's 3 steps done. Next up, the last one, submit the pull request. So you've toiled away now in the darkness for what seems like months in your little cave, and your fingernails are long and there's scratching on your keycaps and your clothes are all tattered and torn. But you finally found the perfect solution, and so you emerge from your cave victorious. Now what? What do you do? See, this is probably the most complicated of the steps that I've outlined so far. It's an appropriate final boss, if you will. But even if a pull request might be conceptually fairly simple, but it's still an intricate thing to do, luckily it doesn't require intimate knowledge of Git. Now, I've been talking about Git this whole time, and I realize that there are other versioning control systems out there. However, in my experience, Git is usually what you'll run into, so that's why I'm talking about that. But there are others. I know. So, as I mentioned during the last step about using the contributing file, about making sure that your commits are in order, that things are right, just double check that and make sure you haven't left any vanities in the code, in comments, in commits, or anything, because that doesn't reflect well on you. Don't. Yeah. Some projects might wish you to squash your commits before you contribute. Again, this is part of the contributing file, and if you didn't know, squashing commits means you take a bunch of them and just squash them down into one giant commit with all the changes. This can get technical, and I'm not going to really talk about it here, but do know it might go wrong. Last time I did that, I had to create a new branch and just do everything all over again. I didn't lose any work. I just really messed up my current branch. Opening a pull request is usually done through a button in the web UI of one of your source forges, so it's a fairly simple thing. So as long as you've gotten this far and you've opened the pull request, you've made your changes, and it's all here, the next step is to get feedback from the maintainers. And this is the scary part. This is when you've got other people looking at your code and reviewing your code and making sure that you're good enough. Except it's not about whether you're good enough, it's about whether your code is good enough. And it's scary. There is, perchance, a lot of imposter syndrome going around in open source and in software in general, and you might feel like, I'm not sure it's good enough. But believe in yourself and trust that, yeah, if you've made the changes and it works and you follow the guidelines, it's good enough. And often you'll get feedback saying, hey, this looks good, but they'll have a couple of things to change. And this will be about maybe reusing patterns that exist other ways, other places in the code base, or maybe it is about, well, this doesn't quite conform to our code style, or so and so they might have some feedback for you, or maybe they think about this one edge case that maybe you haven't covered. Listen to them, and just bear in mind that they're not really critiquing you, they're critiquing your work, and it's not to be, it's only to make the project better. It's not for any other reason. So assume good faith from the maintainer and listen, but also feel free to discuss and stand for your choices. And especially if you thought about it, maybe you just haven't thought about it, and that's okay, we'll change it. But if you say, I think this is a better way to do it, have a discussion and see what comes of it. Assuming now that you've gotten some feedback and you've agreed that, yeah, okay, I'll fix this, you start iterating. You go back to doing some more work, get back into your little cave, sit down, type a little bit more, and then emerge again. This time, you've implemented the changes, and you do this until you've got all approvals and it's all good. Just as a little side note, when you make the changes, you don't create a new pull request, you just update the one you've currently got. But assuming that you've gone through this loop back and forth enough times, or enough times for everyone to be happy, then yeah, the PR looks good and we can land it, as the terminology goes. So congratulations. Give yourself a little pat on the back, a little scratch on the chin, a little pat on the head, whatever you need to feel good about yourself. Just breathe, lower your shoulders. You've cleared the technical part of this talk. Congratulations. Give yourself a self-five. Don't high-five anyone else because right now, yeah, you know. But, and this is important, open source isn't all about tech. It isn't all about the software. Because what's the point of something being open if you don't have anyone to share it with? By contributing to open source and by engaging in discussion around open source software, by talking on issues and engaging with maintainers, you become part of the open source community. And that's really important. So let's talk about the open source community. In fact, let's talk about being a good open source citizen. Because if you're gonna contribute, if you're gonna be part of this, it's important that you try your best to be a good citizen. Not only for your own sake, well, I mean, people will like you better and people will get on with you, but for everyone's sake, for creating a better community. So there's a couple of points here to list. We'll start by saying, follow the code of conduct, if there is one. Much like the contributing file, a lot of projects will have a file in the root of the project named code of conduct. And the amount of projects that have this file is increasing. Now, if you find one, read it and understand it. If you've read one or read two, you've probably got the gist of them because they're usually spawned off from a standard template, but it's important that you follow them and that you are courteous and you're being kind and a good citizen. And if you've read the code of conduct, also, again, read the contributing file. Make sure that your contributions are in line with what people expect. Further on to this contributing file, it contains information for how you contribute. And the reason for it being there is that it saves the maintainers having to tell everyone the same thing over and over and over and over again. If they can write it down once, it's much easier. So now you know how and where to create issues because that's in the contributing file, and you know how to act because that's in the code of conduct. So let's talk about creating good issues. Let's talk about what you need to create an issue that's helpful and beneficial to the project. For an issue to be relevant to the project, for it to be beneficial, it must contain relevant information. It must have what's necessary for people to see it and go, oh, we can fix this because so and so and so and so. As such, and to assist in this, many projects have what's called an issue template, and they'll usually have a few different ones. They'll have ones for features, for instance, where you can say what you want and potentially how you think it should be implemented and any other ideas you've got. And they can have things for bugs, for instance, where you have a short description and you say, I expected this to happen, but this actually happened. And you might also have others for documentation or other forms of issues. Use these because they will help you put down the information that you need and that the maintainers need to look at the issue and to understand what needs to be done. So absolutely try and provide as much relevant information as you can. But at the same time, try and avoid irrelevant information, because if it's just noise, it's really hard to work through and it's hard to know exactly what you're actually looking for. So a good balance here might be to add as much relevant information as you think is sensible. If I would rather err on the side of adding too much than too little. However, it is perfectly fine to say, okay, I've added all the information I think is relevant. If you need anything else, let me know, and I will be happy to provide it to you. Remember, it's a dialogue. It's going back and forth. It's not just a one-way thing. It's not just, here's the issue and that's it. Usually, you'll want to have a dialogue with maintainers and talk about how can we fix things and what's wrong, and answer questions and, posit more questions to them. And when we're on engaging with maintainers and creating issues, a big no, don't do this. And that's don't insult the project. This, this might seem obvious, but you'd be surprised at the things I've seen, and I've hardly seen any of it. So do not insult the project. It is okay. It is perfectly fine to be frustrated, to be confused. If you spent an hour or a day trying to make something work, but you can't because the documentation just isn't good enough, or something just doesn't work the way you want it to, it's okay to be frustrated. And it's okay to say, I'm frustrated because I've been trying to do this all day, but I can't make it work. Or I'm confused. That's fine, but don't say, this is stupid. Don't actually insult the project. It's okay to say things aren't as good as they can be, but don't do it in a very negative way. Don't say, this is stupid, this sucks, let's throw it all away, this is garbage. Because people do that, and it's not great. But if you don't want to insult it, what you do want to do is provide compliments. Give compliments where applicable. Everyone likes getting compliments. Everyone likes having their ego stroked every once in a while. And everyone likes seeing that people enjoy what they create and what they maintain. So by showing appreciation for the project, you instantly make the maintainers that much more likely to interact with you in a positive way and to want to help you. And it also shows that you genuinely enjoy, or that you are invested in the project. If you can say, hey, I've been using this daily for so-and-so, and it saves my bacon every day, or something like that, where you can show that you actually use it and you like it and you care about it, and that's why you're reporting it. It's just that much more useful and that much more helpful, and so much easier to have a positive conversation. Also, if you see a bunch of PRs that are stuck, that have been stuck for ages, that are just sat there and nothing's happening, either one or many, remember, this does happen because maintainers are busy, contributors are busy, maybe they can't quite agree on what the way forward is, and maybe they're just waiting because someone's going through something right now, so they'll fix it, but it'll be a week or two or so. That's okay. Be patient. Have time. Things aren't instantaneous. They take time. So in addition to being patient and being courteous, in a world where you can be anything, be kind. And this needs saying more than it should, but it does. Remember the human. When you're interacting with someone, they're not just an avatar and some text on the screen. They're not just this little speech bubble or this little rectangle with text in it. They're real people. They have real lives and real jobs, real friends and real family, just like you and just like me. Remember this, and they probably work on the project in their spare time. They're probably not paid for it. Yes, there are certain maintainers that are paid for it and who work on it as a full-time job, but the majority, I think, don't. Be aware of this and understand that people might have lives outside, so things take time. And also, if someone comes across as rude, before you take offense, it's fine, and it's perfectly acceptable, but before, just take a little step back and think, they might just be having a very bad day. Maybe something's just gone really sideways for them that day, and then this thing happens, and or maybe they want to clear it out, or just get their mind off it, and they start responding to you. I don't know about you, because I can't see you and I can't hear you, but I know that for me personally, if I'm having a really bad day, then sometimes, yeah, that does leak out into interactions with other people who aren't actually part of whatever's going on that day. Also, maybe they just didn't think about the wording. Maybe they didn't think about how they put it. In text, short and sharp can come across as very rude and off-putting, even if it wasn't meant that way. Maybe they just want to be brief and say, this needs to be done. But it's hard when you don't have body language, when you don't have tone of voice to underline what you're saying. And also, English, or whatever language you're speaking, might not be the first language. It might not be the second, third, or even their fourth language. Maybe they don't speak this language at all. Maybe they're using a translator to interact with you. 2 days ago, Jørgen Kvalsvik, the maintainer of Segway, in his talk, An Almost Free Lunch here at NDC, mentioned that he had an issue opened by a Chinese contributor in Chinese. Now, from what I understand, Jørgen doesn't speak Chinese, he doesn't read Chinese, so they used Google Translate to communicate with this person. In the end, they solved it, and it was to do with Chinese file names or non-ASCII file names not being treated correctly on Windows. And that's a great thing to get sorted out. But in this conversation, when you go through a translator, I think we're all aware that it's probably not the most eloquent Chinese that came out at that end. So keep that in mind. Before responding negatively, make sure they meant it that way. And try and put yourself in the shoes of the maintainer or the person on the other end. Again, referring back to Jørgen Kvalsvik, because he had a really good talk about just this. Most of the interactions I have with users are wonderful, he says. And I love the community to death. That's a positive thing, that's a positive thing. And I think that's really important, and it's how we should think about them. However, sometimes people are entitled, sometimes people are lazy, and honestly, sometimes people just are nasty. It's a shame, but it happens, and we must acknowledge it, that some people are just bad actors. Maybe they don't have good people skills. There's a lot of this around in tech, and there's stuff like elitism, where people use massive big words to try and appear really important and show that they know what they're talking about, and you probably don't. And it's really toxic is the word for it. Sometimes you need big words, absolutely, but you don't always need them, and there's a time and place for it. Now, remember the code of conduct that I mentioned earlier. There are communities where they've actively fought against getting one instated, where they've said, we don't want one. And that's just mad, because it's there for us to show respect and to engage with each other in a productive manner. Some people really are just bad seeds, and sometimes you can't change it. Sometimes that's just how things are, and you need to know when to walk away. The easiest way to deal with a project where you don't feel welcome or where people are toxic is you stay away from those projects. Try and find communities where everyone is welcome. Finding welcoming communities in tech can be hard, but it is really, really important. You should find a place where you feel welcome. Find a community where you feel like you can contribute and where you can help, and create a community that is welcoming not only to you, but to others. Now, a large part of this is welcoming minorities and underrepresented groups. In general, tech, and open source as well, skews heavily towards white and cis male. And this is a problem that we must acknowledge. As Dylan Beatty pointed out in his keynote here on Wednesday, we need more diverse people. We must do better. Greater diversity helps us create better software and more robust communities. And there's so much discrimination going on out there right now. And if there's anything we've learned from the past few weeks and the events over in America particularly, it's that racism is still alive and it's still well. And it isn't exclusive to the American justice system. It is everywhere. So we must do what we can to fight against it. To anyone watching, to anyone listening who identifies with an underrepresented group, know that you are all welcome and you're all wanted, you're all needed. We need you to create a community that fosters diversity and that is really the best that it can be. Now, yes, of course, it's easy for me to say I'm privileged and I'll never really understand, but I want to help and I want to stand with people. I want to stand with you. I don't have the right to speak on anyone's behalf, but what I can do is I can listen. I can encourage other people to listen. Listen, keep listening. And when you think you're done, listen some more. Show support and amplify their voices. Be a positive force for good and to open up and welcome everyone. Because representation matters. Representation really makes a difference. And if we don't actively work towards it, we'll never get there. This might not change the world all at once, but it's a step in the right direction. So, in short, for communities, for the actual really important part of open source, remember, be kind, be excellent to other people, be what you want other people to be towards you. Be patient and be forgiving. Try and understand, but also know when to walk away. Remember the human on the other side of the screen. Remember that they're people just like you, with troubles and worries just like you. Be welcoming, be open, and together, let's create a better community. Thank you very much. That was the end of my talk. I will now go over into Slack to see if there are any questions. I'll answer them as we go along. Let's see what I can find. Woo. Oh, yep. Not much happening on WebEx. What's the YouTube link? Yep. That was asked at the very beginning of the talk. Now, there's no other questions in here right now. If anyone wants to get in touch with me, you can reach me on Slack for the rest of the day and for as long as this Slack team is open. If not, feel free to reach out on Twitter or any other platform and I'll try and respond as timely as possible. So thank you very much for spending this hour, these 50 minutes with me. It's been a pleasure. I hope your day is wonderful and that you enjoy the rest of the conference. Thank you very much.
Good morning, everybody, and welcome to the virtual Room 1 at NDC Oslo 2020. My name is Mark West, and I'm going to be deconstructing deep learning with you this morning and, well, the start of the afternoon. And before we begin, a little bit about who I am. So, I'm a Java developer and architect, and as you may hear from my accent, I'm British, but I've lived in Oslo for quite a while. And I work at a consultancy company called Bouvet, where I manage a team of data scientists and data engineers. And in my spare time, what's left of it, I'm actually an active member of JavaBin, the Norwegian Java user group. So we go around and do all kinds of things, meetups and conferences and whatnot. But enough of that, let's get on with the talk. So today, as I said before, I'm going to be introducing some concepts behind deep learning to give you a bit of a kickstart into this very exciting field. My talk is split up into 3 sections. The first section is going to focus on Deep Learning 101. So I'm going to try and give you some basic understanding of how deep learning works and what it is. Then we're going to look at a specific neural network architecture or deep learning architecture, convolutional neural networks. Now these are very good at dealing with spatial problems and therefore very good for image processing. And then finally we'll wrap up with by looking at another type of neural network architecture, recurrent neural networks. And these are very good with serial data or time series. So they're particularly good at processing text. So let's get started with the first part of the talk, Deep Learning 101. And to really understand, well, the first thing we need to do actually is define what deep learning is. And deep learning is biologically inspired machine learning based on multi-layered artificial neural networks. Now what does this mean? I've got 2 pictures here, 2 GIFs on the screen at the moment. Now the one on the left is the picture of a brain rotating around, and you can see activity in the brain. Now the theory about how the brain works is that the brain is comprised of billions of cells or neurons. And these are organized into hierarchical groups. And basically, they're all connected to each other. And when you activate one neuron, it will send on activation to other neurons and so on and so forth in a kind of cascading activation across the brain. And the theory is that helps us, well, it makes us what we are. It gives us intelligence, helps us react to things, gives us the ability to see, hear, reason, and so on and so forth. Artificial neural networks are based on that theory. So artificial neural networks are a set of computational nodes that perform simple mathematical functions that are organized into hierarchies and connected up to each other. And they allow computers to learn and do things which, basically seem intelligent. Now, neural networks basically comprise of nodes and connections. And in this picture I'm showing you now, this GIF, you can see the nodes, they're the orange circles, and the connections between them are the black arrows. And this picture here is of what we call a multi-layer perceptron. In other words, it's a set of computational nodes organized into 3 layers. And as you can see, what's happening is information is coming in to the left of the network, and it's passing through the network, activating the nodes on the way, and then you get some kind of result at the end. Now this is a feed-forward architecture. As you can see, information is flowing in one direction. It's flowing from my left to my right, or your left to your right, in fact. And this network is densely connected. In other words, it means that each node is connected to all of the nodes downstream. This means that when you start dealing with big neural networks, which are containing maybe hundreds of thousands of nodes, you would have a large amount of connections between those nodes, and that can really raise the computational complexity of your network. Another thing I just want to mention quickly is that the connections in these types of networks are weighted. In other words, the connections can amplify or dampen specific inputs. And I'm going to explain more about that in just a couple of slides. Neural networks are generally organized into layers. And there's 3 basic types of layers that I want to inform you about. The first type of neural network layer is the input layer. This is where information comes in to the neural network. Now, an input layer is basically the contract. This is where we define the shape of the data that we want to allow to come into the neural network. A good example might be if you have a picture of 10 by 10 pixels, a grayscale image of 10 by 10 pixels. That's one value per pixel. So then you would need 10 by 10 pixels or 10 by 10 nodes in your input layer to take that information in. In other words, you need 100 nodes in your input layer. And the input layer doesn't do anything else. It just provides an endpoint for which your client can call your neural network. Information is then passed on to the hidden layer. Now, the hidden layer is where the magic happens. What the hidden layer is going to basically try and do is going to try and correlate between the given input and the desired output when you're training the network. So if you're showing the network a picture of a cat, the hidden layer is going to work out, okay, what do I need to find in this picture to say this is a cat? So that's what the hidden layer is doing. That's where the learning is taking place. And the hidden layer is so cool because it's actually not exposed to the outside world. After the hidden layer, you have the output layer. This is where the output comes from the neural network. And this is going to deliver the end result. So the output layer needs to reflect your use case. So if you just have a simple true or false output, then it's okay just to have one node, maybe with a value from 0 to 1. But if you want to find 10 different types of animals in pictures, you're going to need 10 nodes in your output layer, each one of those nodes representing one of the animals you're trying to find and giving the probability that that animal has been found in the picture you've just given it. So deep neural networks are basically artificial neural networks with more than one hidden layer. That's it. This does not mean that deep neural networks are more intelligent. It means they're more complex. But it also means that, like, when you have multiple hidden layers, you can delegate different jobs to these hidden layers, as we'll see later on. So now we understand the overall architecture of the neural network, but we don't really understand what's happening with all of these nodes. I mentioned before they're computational nodes and they're doing simple mathematical calculations. But what does that actually mean? Well, let's just look at an artificial neural network node and try and understand what's going on. The first thing to remember is there's lots of inputs coming into a node. There could be literally hundreds of thousands of inputs coming from the previous layer into a given node, especially in a densely connected neural network. And all of these inputs that are coming in will be weighted. In other words, they will have weights assigned to them that will amplify or dampen the input's strength. Now, this is how a neural network trains. By adjusting these weights, we can actually train a neural network. We can get the neural network, for example, to be more focused on the features that make up a cat than the features that make up a dog. All of those weighted inputs come into our node. And the first thing that happens is they're all summed up. They're all added together. And then that sum of weighted inputs we push through a simple mathematical function called an activation function. And that activation function will decide what kind of output the node will give out. Now, if we look at how the human brain works, cells in the brain, they have a threshold, and once that threshold is exceeded, they will fire. That's the same kind of thing that an activation function is doing. And then the output from the node will be sent to the next layer of the artificial neural network. And this output could be spread to literally hundreds of thousands of nodes in the next layer. So that's basically how a neural network node works. It takes in inputs, those inputs are all weighted, it takes them all in, adds them together, and then decides what kind of signal will I push on further in the network by using an activation function. So a little bit about activation functions. Now, I try to avoid mathematics in this talk, but we are kind of stepping into that territory now when we talk about activation functions. What an activation function does, in simplest terms, it converts an input into an output via some simple calculations. And there's many different types of activation functions out there. So I'm not going to go into great detail about them, but I'm going to give you 3 examples of activation functions and try and explain how they differ. So what I've done here is I've drawn a simple grid on the slide, and basically I'm mapping the output value or the input value to the output value, and I'm just assuming the input range is from -1 to 1. The first type of activation function that we'll look at is a sigmoid activation function. And what the sigmoid activation function does, it gives a value, or gives you an output between 0 and 1. So this is a good one if you want to look for something true or false, right? And so we see here is if our input is -1, then we get 0 out. If our input is 0, then we get 0.5 out. And if our input is 1, we get 1 out. So what we have is we have a nonlinear relationship between the input and the output of this activation function. And this is similar for the next type of activation function we'll look at. This is a hyperbolic tangent activation function. The difference between this and the sigmoid activation function is that it has a higher or wider output range. It goes from -1 to 1. It centers the data on 0. And then we have another type of activation function. This is called a rectified linear unit. And all this one does is a simple if then else statement. It says, if the input is less than 0, round it up to 0. Otherwise, just give out the input that came in as the output. So the rectified linear unit is very good at just removing noise, removing all minus values from your data. Now there's lots of different activation functions out there. The behavior and the pros and cons is very based on your use case. But I just wanted to give you an idea of how they look and how they work. So now we understand what a neural network looks like. It's comprised of layers, nodes. We have activation functions deciding how information is sent through the network. We have weights. But how do we train this? How do we train an artificial neural network? What we do is we give it training data. So in this example here, I'm training a neural network to tell me if it sees a cow in the picture. And I'm going to show this neural network lots of pictures of cows. And the neural network, while I'm training, is going to make its best guess. It's going to generate predictions, which are numeric values. And as we see in this example, I'm getting a numeric value out, which is a probability score, like 0.15 chance that this is a cow. In other words, this isn't a cow. So the network isn't doing a very good job. So we generate these predictions, and then what we do is we compare the predicted output, or the output we got from the network, with what we wanted to see. So this is a kind of supervised learning. So these values are numeric, so we can actually subtract the predicted value from the expected value and calculate a loss. So a loss function calculates the difference between what the network predicted and what it was expected to predict. And that loss function, the bigger it is, the bigger the error. So then we can use that loss function to update the weights. The result of the the loss function will be passed backwards through the network, updating the weights in a process called backpropagation. And the idea is that we're going to fiddle with the weights and try and adjust them so that the next time the network sees the same picture, that we have a lower loss. In other words, we have a closer match between the predicted and the expected value. And that's basically how we train neural networks. It's just like showing pictures to a child and saying, who is this, and who is this? And eventually they'll remember who you're showing them. Or when you train kids to recognize sheep in picture books when they're kids. It's a very similar process. Now, how do we update the weights in the neural network? How do we do that? How do we know which way to turn them up or down to get the best results? The answer is we don't. We don't have a map. So it's a kind of a case of trial and error. How we actually update weights in a neural network is through a process called gradient descent. And what I've drawn here is a simple little graph which shows you different possible loss values for different weight values. This is a gross oversimplification of what's actually happening, but it's a good visualization. So what happens is when we start training the network, we might be here where the start flag is. So in other words, that we have a certain setting on our weights, but we have a very high loss. And what we want to do is we want to find our way down to the bottom of this hill. But we don't have a map. And we're basically blindfolded. So you imagine being on the top of a mountain, you're blindfolded, and you want to find your way down the bottom of a hill. How do you do it? You pull out your foot and you try and take a step downwards. You don't go upwards, but you always try and go downwards. And that's basically the same as what gradient descent does. It makes small adjustments to the weights to try and take the value of the loss down. And the amount of adjustments to the weight is called the learning rate. So if you want to take small steps, you have a low learning rate, or a small learning rate. If you want to take big steps, the opposite. Now, if you take big steps, what can go wrong is you can hop over the global minimum and end up in the local minimum. So this is the challenge with tuning the learning rate. If you take 2 small steps, it takes forever to get to the bottom of the hill. But if you take two big steps, you might jump over the bottom of the hill and end up in a local valley, which is okay, but not the optimum or not the lowest place to be. So now we've come to the end of the first part of the talk. What we've covered is that an artificial neural network is a set of interconnected nodes. Those nodes are organized into layers, the hidden layer, the input layer, and the output layer. And deep learning refers to artificial neural networks with multiple hidden layers. Inputs to nodes are amplified or dampened by weights, and those weights can be tuned or adjusted using gradient descent to optimize the artificial neural network's predictions. Okay, so now we've done the machine learning, or should I say deep learning 101, we can now move on to convolutional neural networks. We can actually start looking at real life neural networks. Now, convolutional neural networks have really been a revelation in that they are very efficient and they're very powerful. And as I mentioned before at the beginning of the talk, they're spatially aware, so they're particularly good for dealing with image processing. And that's what we're going to talk about here. We're going to talk about using convolutional neural networks for image processing. But before we go into the detail about convolutional neural networks, I want to look a little bit at some background information. Now, first I want to start with reminding you how computers see images. So here we have a picture of an ankle boot. It's a 28 by 28 pixel picture of an ankle boot, and it's a grayscale image. So there's 1 pixel value per pixel, 1 value per pixel. So in other words, I think 784 individual values in this image. And that's how computers see images, as a grid of pixel values, not as, not as the way we do. It's basically looking at this as a set of numbers. And this means that the amount of numbers involved in processing images quickly becomes very, very high. So if we have a grayscale image like the one I just showed you, 28 by 28 pixels, it's 1 channel, so 1 value per pixel, we have 784 values. But if we have a color image of the same size, 28 by 28 pixels, we'd have 3 pixel values per pixel. We'll have the red, the green, and the blue saturation. So we end up with 3 channels. So we end up with 2,352 values. That may not seem like much, but we're dealing with an image that's 28 by 28 pixels. When you start getting to big HD images and ultra HD images, then the actual complexity, the amount of data in the image is very, very high. And this has always been a challenge for when you're dealing with image processing using multi-layer perceptrons or traditional deeply connected neural networks. And I can show you an example of why this is a problem. Here we see a picture which is like, say it's for the sake of argument, it's 640 by 640 pixels, and it's color, so it has 3 channels. There are more than 1.2 million pieces of information in that picture. So that means that if you send in this picture as it is into an artificial neural network, you'll need over 1.2 million nodes in the input layer. Now imagine you have a hidden layer which has around about 1,048 nodes that is going to try and work out what this picture is of. The connections between the input layer and the hidden layer in a densely connected network will be nearly 1.3 billion. All of these weighted connections need to be calculated. When you send the image through the network, you will have to create the weighted values for each one of these connections. You'll have to update these weights every time you're training the network. You'll have to use the weights also when you finish training the network and when you're actually using it in prod, you'll still be using these weighted connections. So the amount of processing power required for a 640 by 640 pixel image is relatively high. And that's always been the problem with multi-layer perceptrons. They require far too much processing power, and also it takes too long. It takes a very, very long time to do all this kind of processing. So this is where convolutional neural networks have become popular. And convolutional neural networks, they basically eat the elephant up one bit at a time by using something called convolutional filters. Now I'm showing you a couple of convolutional filters on the screen now. One is a vertical edge detector and the other one is a horizontal edge detector. And they're basically small grids of values. And what they do is they amplify specific features in images. In other words, if you want to amplify shadows, specific colors, lines, and so on, these filters will do that. And they're reusable. So in other words, these are 3 by 3 pixels, in other words, 9 values. You can slide them backwards and forwards over your big images to find or extract the features that are interesting for your neural network to see. What's more, these are weights that can be learned during training. So in other words, your neural network learns which filters it wants to use by trial and error. So it means that like these filters can actually be reused later on. If you train one neural network with blank filters, you can actually take the filters that it learns and use them in the neural network in a process which is known as transfer learning. So a convolutional neural network will generally have lots of convolutional filters. Each one is going to be looking for a specific feature in your image. So let's look at an example of how you can apply convolutional filters, or how they're actually applied in the convolutional neural network. We have a convolutional filter here which has been trained. This is good at finding lines on the left-hand side of an image. It has a size of 3 by 3 pixels. It has a stride of 1 by 1. In other words, it will move 1 pixel in each direction as it slides across the image. Here is an original image that we're going to look at, and this is a very simple 6 by 6 pixel image of a black square. And the result of using the filter against this image is going to be a feature map. In other words, a filtered version of the image which brings out specific features that we're looking for, in this case, a line on the left-hand side. So the convolutional filter is applied to the image. It starts in the top left-hand corner, and what it does is the values of the filter are multiplied by the underlying pixel values, and then they're added together for all of the 9 pixels that are under the filter. And the result is 3. The filter then moves 1 step to the right, 1 step to the right again, and 1 step to the right again. At this point, it's reached the edge of the picture. So this is why this feature map will be 4 by 4, because the convolutional filter can only move 4 steps in each direction across this. There is ways to actually fix that, but we're not going to go into that in this talk. The filter then moves 1 level down and starts doing the same thing again. And once it's finished, we end up with a feature map. And this feature map is a set of numbers which shows us that the neural network has found something on the left-hand side of the screen. The numbers that are minus on the right-hand side of the screen, there we can look at them in this particular case as noise, and they will actually be removed. So what we'll do now is we'll apply a rectified linear unit activation function to our feature map that we just generated. And the rectified linear unit activation function, if you remember, it takes away all the minus values. So we end up with this new feature map on the, let me see if I can use my, on the right-hand side here, which is showing a line here. Then we can actually do another step to further reduce the amount of data going to the neural network. Why do we want to do that? Well, if you remember that picture I showed you of the budgie, remember the more data that goes into the neural network, the more processing power it needs. So if you can reduce the dimensionality or reduce the amount of input going in, you can actually speed up the network. The danger of doing this is that you can actually reduce the dimensionality so much that you remove the features that your network needs to work. So this is a bit of a fine-tuning process. But anyway, pooling allows us to reduce the size of our feature maps even more. So we have a pool here which is 2 by 2 pixels, has a stride of 2 by 2, which in other words means it will move 2 pixels in each direction as it slides across the image. We have our feature map that we generated in the previous step, and we can apply 3 different types of pool to a feature map. I just want to show you how they work. And these pools will generate different types of feature maps. We have max pooling, average pooling, and sum pooling. And when we apply the pools, these pools, to our feature map, max pooling will take the maximum number in the pool. Average pooling will add the numbers together and divide them by the size of the pool. And sum pooling will just add them together. And we see that the pool moves 2 steps across because it has a stride of 2. Does the same calculation, 2 steps down, 2 steps across again. So we see how these new feature maps, which are much smaller, still have that information about that line on the left-hand side of the screen. So just to recap, we started with a picture of a square. We applied a convolutional filter to it which found a line on the left-hand side. We removed noise from that feature map, and then we used pooling to reduce the size. And what will happen in practice is you'll have lots of different feature maps all finding different features. And once those features have been extracted by the convolutional filters, they can then be passed further onto the network, to the dense layers, for matching against a specific category. So that's how convolutional neural networks eat the elephant, one step at a time. They first define all the features or find the features, and then they send them further in the network for further processing. So let's try and look at a convolutional neural network in context of a real life use case. And the use case we can use is the fashion MNIST use case. Now, fashion MNIST is a data set that was created by Zalando, and it contains 70,000 labeled images of clothing. And those images are very, very small and simple. They're 28 by 28 pixels. They're all grayscale, so one value per pixel, 784 values per image. And there are 10 classes of clothing in this data set. You have ankle boots, I think pullover, t-shirt, shirt, that kind of thing. And the data is distributed evenly across these 10 classes. So you have 7,000 pictures of shoes, 7,000 pictures of sandals, and so on. And what I did for the sake of this talk, I trained a very simple convolutional neural network on this data set. And the convolutional neural network can tell us which class a given image belongs to. And for those of you who like to look at code, you can actually find the code at my GitHub. I'll share this link on my Twitter afterwards for those of you who want it. But if you go to my GitHub, you will find a notebook which you can click on. And when you click on it, it will open it up in Google Colab. Google Colab is Google's hosted Jupyter notebooks. So in other words, you can run my code in Google's hosted notebooks against their hardware. And yeah, it'll just do everything through the browser. The neural network I've created is created using TensorFlow and Keras. It's actually an old version of TensorFlow. I think at the moment it's I can't remember which one, but it's version 1 of TensorFlow, so it needs to be upgraded to version 2. But still, it still works, and you can get a good idea of how neural networks are put together and the kind of pre-processing you have to do to actually get them to run. This code also includes some good code for visualizing what the neural network's seeing, and I'll show you some examples of that later on. So we can see that this neural network, we have a, let me see if I can find, here we go. This is the neural network here. So we have 1, 2, 3, 4, 5, 6, 7 layers. And we're going to step through these layers now and explain what they're all doing. So here's another view of the neural network. We have our input layer. We have 5 hidden layers, which means it must be really smart, and an output layer. Now, the input layer is just taking in our images. They're 28 by 28 pixels, as I said before, with 1 value per pixel, 784 values. And the images are sent into a convolutional neural network in 2 dimensions. Or, well, for a grayscale image, it'd be 2 dimensions. If it was a color image, it would be 3 dimensions because you'd have the 3 channels. So the information comes into our input layer, and it's then processed by a convolutional layer. And the convolutional layer will learn during training, it will learn a set of filters, and after training, it will apply those filters to the images that will generate feature maps, you know, the lines and the edges and the shadows that we need for the rest of the network to use. The feature maps will then be pushed through a max pooling layer. The max pooling layer will reduce the size of them, like I showed you just a moment ago. So these first 2 layers in the hidden layer, or these first 2 hidden layers, they're all about extracting the features, right? They're all about finding those lines and extracting them to help the neural network work out what it's looking at. The next layer is more of a, well, you could call it housekeeping layer. It's a dropout layer. Now, the dropout layer will randomly disable 25% of nodes in this layer. So basically, it mirrors the max pooling size and structure, but it randomly deactivates 25% of the nodes in each training run. Why would I do that? Well, I'm trying to force my network to learn different paths to solutions. And this is to try and make the network more generic. I'm actually trying to fight something called overfitting here. Overfitting is when your neural network just memorizes the training data. What we want it to do is generalize based on the training data so it can do a better job when it actually gets tested on data it's never seen before. The next layer is another housekeeping layer. This is a transformation layer. All we're doing here is we're flattening our data from 3 dimensions to 1 dimensions. Now, at this point, the data that comes in here is a set of feature maps, which are, by this time, I think they'll be 26 by 26 pixels. and there's 32 of them. So it's 3 dimensions of data. Dense layers don't like 3-dimensional data. They like it all in one simple list. So the flattened layer will just convert my 3-dimensional data into a 1-dimensional list. And now we're ready to pass our data into the dense layer. And if I remember correctly, this dense layer has 128 nodes. And this layer will decide what it's looking at. This layer will try and work out, am I looking at a square? Am I looking at a house? Am I looking at a car? And in the final layer, we have our 10 nodes, which are the nodes which tell us, okay, what is the network predicting? So we have actually, I mentioned cars and houses and that, but this use case we're looking at here is clothing, right? So we have 1 node for sandals, 1 node for ankle boot, 1 node for t-shirt. And each of those nodes will predict a probability or give us a probability of that it's actually found that item in the image. For fun, I actually, after training my neural network, I chopped it up so I could actually visualize what the convolutional layer and the max pooling layer are seeing. And here we have an example of after the network's been trained, and I feed in a handbag, a picture of a handbag, which is like from my Zalando training set. That comes into my convolutional layer, which is going to apply 32 trained convolutional filters to the input image. And I end up with these 32 feature maps. And here you actually see what I've been trying to get across all this time is that like the filtered images are like different versions of the original image that all bring out different details. I particularly like these 2 here because it looks like 2 pictures of the handbag from different angles, but it's just basically filters that highlight different edges. I like this one as well because it just gives you an outline, an overall outline, while this one here gives you more information on the details of the handbag. So this is how convolutional neural networks work. They filter the image and they generate different views of the image, which make it easier for the dense layer to work out what it's looking at. And the max pooling layer reduces the dimensionality, as I've said before. So here is the set of feature maps we just generated. And I push them through a max pooling layer with a stride of 2, with the aim of reducing the size of the feature maps via feature pooling, and I end up with this. So I still have the same values or the same images, but they're slightly more pixelated. But I've managed to keep the details that are important for the neural network to work out what it's looking at. So training and testing this neural network was a relatively simple job. I have 70,000 observations or examples. So what I did is I split my data up into training data and testing data. A word of advice, you should never test your network with data it's already seen. You should always test your network with data it hasn't seen. So that's why you split your data into training data and test data. And I trained my CNN, updating the weights via backpropagation every 256 records. I'll do this 10 times. So I run through my 60,000 training examples 10 times. And this takes probably about 3 or 4 minutes on the Google Colab, when you run the code on Google Colab, the code that's available from my GitHub. And then I test the data with test the CNN with test data and score it based on accuracy. How close were we to what we wanted to see? And here are the results. And we see that we have our different items of clothing here, and we have different percentages, which give us an idea of how well our neural network performed with test data. There's a lot of different values here, so I just want to explain what they all are. We can start with precision. Precision refers to the amount of correct class identifications. So in other words, is basically for all of the, how many of the t-shirts that I said were t-shirts were actually t-shirts. So precision should be used when the cost of false positives is high. So you can think about precision is important when you're dealing with spam emails. Because if you say, oh, that's spam, but it's not, then that email is going to get put into the junk file and no one's going to read it. So that's an example of where precision is important. Then we have recall. And recall is the percent of correctly identified class members. So in other words, for all of the t-shirts in my test data set, how many did I actually find? How many did I actually say were t-shirts? That's recall. Now recall is important when the cost of false negatives is high. And a good example of that, which is quite up to date, is COVID. If you get tested for COVID and you're told, oh, no, you don't have it, then you go and you do have it, you can go out and you can spread it around. So that's an example where recall could be important. Now, a lot of people get confused about the difference between precision and recall, including me. So like a lot of people just say, okay, let's just use the F1 score, which is the harmonic mean of recall and precision. And then you have the overall accuracy, which is the overall accuracy for the whole network. Here's some examples of incorrectly classified images. And when you're doing some training, it's always good to see, or when you're doing testing, it's always good to look at your test data where the network got it wrong and try and work out maybe if there's something we can do with the network to make it better. And there's some good examples here. I particularly like this one here. So the network said this was a t-shirt, and it's actually a shirt. Now we can see there's buttons down here. So maybe the network needs to be a bit more better trained, or maybe we need better training data so the network can distinguish between t-shirts and short sleeved shirts. Another example here is this one here. It's actually an ankle boot. And there's a pattern here. You can see this little pattern here. This was predicted to be a sandal. And you can understand why that might be, right? And then finally, this one down here, this is like something Liam Gallagher would wear. It's a coat with a hoodie coat, and it was predicted to be a pullover, but it's actually a coat. So you can see that sometimes it's not necessarily the network's fault. Sometimes the data itself is ambiguous. And that's something you need to be aware of when using neural networks, especially for image processing. So we've come to the end of my session about convolutional neural networks. We're going to move on to another type of neural network in just a second. But to summarize convolutional neural networks, they're spatially aware and they're good for image processing. They use learnable and reusable convolutional filters to identify images features in images. And what's good with these convolutional filters, if you learn them for one neural network, you can actually save them and then reuse them in another neural network, and that would be transfer learning. Convolutional neural networks require dense layers to map the features to classes. And pooling is an optional step to reduce the dimensionality of the input data. In other words, we reduce the amount of numbers that are going through a neural network and maybe make it a little bit more efficient. But watch out for things like pooling, because they can actually damage things by removing the information your neural network needs to make the correct predictions. And then finally, precision, recall, F1 score, and accuracy are different types of metrics for measuring your model's performance. So make sure that you're using the right metrics to measure your model's performance based on your use case. Okay, now we're on to the final part of the talk, and we're going to talk about recurrent neural networks. Now, recurrent neural networks are a different type of neural network architecture, which have a specific goal. They deal with problems like this one here. Which way is the arrow moving? Well, here we have a video or a GIF, and a GIF is basically a set of still images played in sequence. So you need to really understand what's happening, or not. You don't just need to understand the image itself, but you have to understand the sequence of images and how they relate to each other to see that the arrow is moving from one side of the screen to the other. Another example of a sequential problem is understanding text, because generally, when you're reading text, you need the context that comes from the words before to understand a specific word. And the overall context requires an overall understanding of the entire text. So when I was at university, I remember a lot of times I was always reminded by my tutors to read the whole question before answering. And that's a good example of why you need to understand the sequence of the words, that the words come in. But traditional neural networks don't deal too well with this. They don't deal well with sequential data because they experience everything at once. And therefore, they're not very good at handling time series type problems. So this is where recurrent neural networks come in. Now, recurrent neural networks are a family of neural networks with many different types of implementation. But general recurrent neural networks are based on having a persistence layer or persistence in the hidden layer. So basically, it's like a loop in the hidden layer, which is maintaining the state of the hidden layer between sequential inputs. So what happens with a recurrent neural network is that you will feed it a time series. It will take the first sequence in the time series and feed it through the network to the hidden layer. The hidden layer will maintain state between each time series iteration coming through. And then finally, when everything is done, the output layer will give a final result. You can also look at a recurrent neural network like this. Basically, like it's a set of identical neural networks that are sharing the same weights, sharing the same hidden states, and they're being executed one by one in the order of the sequential data. Problem with recurrent neural networks is they are pretty much like me, they have a short-term memory problem. They forget things very, very quickly. And especially if you have a long sequence in your time series, things that happened at the beginning of your time series can be forgotten or neglected in the network's processing. So we need to use a different type of recurrent neural network, a bit of an upgrade to a recurrent neural network for this problem we're going to address today. And that is a long short-term memory network. So what these do, they introduce long-term memory as well as having working memory. So they just add long-term memory to the recurrent neural network. So this means that, like, effectively you have two parallel conveyor belts going through your network iterations, and like some information is on the long-term memory conveyor belt and some information is on the short-term memory conveyor belt, and we have little workers between those conveyor belts that move information between these two as needed. So how is that done? Well, that's done using gates. So if you zoom in to a long short-term memory neural network hidden node, you'll see something like this. So you have your two conveyor belts going through, the long-term memory and the working memory. And then you have these gates, which are basically stacked activation functions that move information between the long-term and the working memory. So you have the forget gate, which will actually remove stuff from the long-term memory if it's no longer important to have that information. Input gate will move stuff from the working memory to the long-term memory. And then finally, the output gate will combine the contents of the long-term memory and the working memory into some kind of output. So the use case we're going to look at today is the Internet Movie Database review use case. This is quite a well-known one, and it actually comes with Keras. You can actually download this data set directly from Keras. And it consists of 50,000 reviews, IMDb reviews, which have been manually classified as positive or negative. And these reviews are encoded as a sequence of integers. So what does that mean? Well, neural networks don't care about words, they only care about numbers. So what we've done, or what Keras have done when they've pre-processed this data set, they've replaced all of the words with numbers. So there's a dictionary, so you can say that like word number 53 maybe refers to the word but, and so on and so forth. The thing is with these numbers is the integer represents that word's overall frequency in the data set. So the word that has the integer of 1 will be the most popular word in the data set. So basically all the words in the data set have been changed to numbers. And the goal is going to be to create a LSTM, long short-term memory deep neural network that can correctly classify a movie review. And here we actually see an example of what the data actually looks like. So on the left-hand side, you see the encoded data. That's what the data set looks like, a list of numbers. But luckily, the data set also comes with a codex, so you can decode the reviews to their original form. But what you'll see is when you do that is that all punctuation, or most punctuation, has been removed. Capitalization has been removed. It looks like a Donald Trump tweet. What we can also see here is the most popular hot word in the whole data set is the start tag. That has the value of 1. And the start tag is just telling us that the review is starting here. Now, I'm going to do some additional pre-processing of this data set to work with it. The first thing I'm going to do is I'm going to reduce the size of the data set, or the vocabulary of the data set, because there are 26,000 different or unique words in the data set. So I'm actually going to reduce that down to the most popular 10,000 words. So all words that have a value of over 10,000 are just removed. The reason to do that is I just want to reduce the size of my training data and try and make my network more efficient. Another thing I need to do is all these reviews are different lengths. And as I mentioned before, the input layer has a contract, right? It wants to see a certain shape of input. So what I'm going to do is all of the reviews that are less than 500 words long, I will pad them out like I did in this example here. The reviews that are more than 500 words long, I'll just truncate every word after the number 500. Another thing my neural network is going to use, which is important for you to know about, is word embedding. Now, what word embedding does is it plots words in a multi-dimensional space. That sounds really kind of like, sci-fi. But basically what it's doing is it's plotting words in a way that we can see the different linguistic relationships between words. This picture here, which is on the left-hand side of the screen, really kind of shows what I'm trying to say here. I stole this picture from a guy called Shane Lin, who has a really good blog about word embedding if you want to check it out. Now, the words in this image that are closer together, they share some kind of semantic meaning. So, for example, bathroom is close to sink, bathroom is close to bathtub, colour is close to paint, finish is close to colour. And you see how this works. We only have 2 dimensions here. Now, mostly word embedding uses a lot more dimensions, maybe hundreds of dimensions. Each dimension captures a specific linguistic relationships between words. The closer they are together in a given dimension, the stronger that relationship is. And there's lots of pre-trained models out there, but I'm not going to use those. I'm going to train my own because I'm stubborn. So here is the link to my LSTM implementation. Again, it's on GitHub. Again, if you click on the actual link, not this link here, but if you open up this link and then click on the link that it contains, you'll get a LSTM implementation written in Google Colab, which will open in your browser. You can run it, you can play around with the code, you can test it out, you can do whatever you want to. Once again, this is written in TensorFlow and Keras. And this is a somewhat simpler neural network. We see here that it only has 6 layers, and 2 of those are dropout layers. So they're just for housekeeping. Now, if we zoom in on the neural network architecture a little bit more, we'll see that we have 4 hidden layers and an input and output layer. Let's just skip through these very quickly and explain what they're all doing. The input layer takes our reviews. Now, our reviews have been, they've had a bit of pre-processing done to them. So they're 500 numbers each, and each one of those words, or each one of those numbers is representing a word in the review. So the input layer takes in those 500 words and feeds it onto the embedding layer. Now, the embedding layer is going to learn 32 dimensions of word embedding for each word in my data set. So this is going to create a lookup table for each word with 32 dimensions of values. And those word embeddings are going to show how different words have a semantic similarity to each other. So the embedding layer is capturing word meaning. We have a dropout layer which randomly deactivates 25% of the nodes during training to fight overfitting. It's exactly the same as what I did with the convolutional neural network. And then we have our LSTM network, or STM layer, sorry. Our LSTM layer has 32 nodes, just 32 nodes. And the LSTM layer takes in both the review, but also the word embedding for each word in the review. And what the LSTM will do is it will learn to differentiate between positive and negative reviews by looking both at the word meaning, the individual word meaning, but also the context that they are in together. Another dropout layer to deactivate or to remove overfitting and force our network to learn different paths to its goal. And then finally, a dense layer. And this final dense layer has 1 node. And that has a single node with a sigmoid activation function, which will give us a value, an output value between 0 and 1, based on 0 being closer to negative and 1 being more closer to positive. To zoom into these 2 of these layers, let's have a look at what's happening in the embedding layer. So the embedding layer, as I mentioned before, is learning 32 dimensions of word embedding for each of those 10,000 words in my training set. And the result is a lookup table that looks pretty much like this. So you have all of the words that are represented by integers, and then you have 32 dimensions of semantic similarity or semantic meaning. And those dimensions are all updated via backpropagation while the network is trained. They're weights. Okay? So this is how the neural network learns. So what this means is a neural network is never really going to understand the meaning of these individual words, but it's going to optimize these values to try and ensure the network gives the best possible results. The LSTM layer takes that word embedding and looks at the word order, combines those together, and then works out the difference between positive and negative reviews. Training and testing LSTM, I took my data set. It's split into training data and test data. So I trained my LSTM with the training data, updating the weights via backprop every 256 records. I did this 3 times, so 3 epochs. And then finally, I tested my LSTM with the test data, which is another 25,000 records with an equal split between positive and negative. And I generate my score. And based on the network that I've just shown you, I got a score of overall of around about 87% accuracy. So if we remember, precision is the percent of correct class identifications. Recall is the percent of correctly identified class members. And the F1 score is a harmonic mean between recall and precision. And if you're still confused about the difference between recall and precision, there are plenty of really good blogs out there which might help you. And the overall score, accuracy, 87%. So I'm pretty happy with that. But we should always look at some of the test data that gave us incorrect results, because that's quite interesting to do. And here is an example of an incorrectly classified review. And this was predicted to be negative, but it's actually positive. And there's a lot of reasons why this might be predicted to be positive, or negative, sorry. For a start, there's a lot of negative language here. You know, the person was disappointed that the show was cancelled, but you see that there is a lot of negative language there, which could drag this review towards being negative. Another thing is there's a lot of these tags. These tags are actually created when the data set was converted from normal words to integers. So these tags also, if they start kind of trending towards being negative, then that's going to affect the neural network's performance. So maybe these tags should have been removed. And also we have some leftover HTML tags. These definitely should be removed, right? So we see here that we have a bit of work to do with the pre-processing of our data. And if we use different strategies for pre-processing our data and selecting which words to include in the training and which words to remove from the training, we might get better results. So to summarize, RNNs handle sequential data by persisting state using a working memory. But that working memory means that it has like a short-term memory problem. So it's often better to use an LSTM, which is a version or a variant of an RNN, which has a long-term memory and resolves that short-term memory problem. Word embedding is a very useful technique for modeling semantic relationships between words by plotting them in a dimensional space. And pre-processing of NLP data is always vital for getting good results. This slide here contains links to a few blogs that I've written about this. If you didn't understand any of the points I was trying to get across, you might be able to get good answers from the blog entries. Definitely go and have a look at the 2 technical implementations, because there you'll really get an idea of how this stuff works. And I promise you, it isn't as complicated as it may sound. Another thing to remember is that I'm not a Python coder first and foremost, so if my Python code makes you cry, I do apologize. Other than that, I will be publishing the slides and everything on Twitter later on today. If you do have any questions for me, ask them on the NDC Slack, and I will answer them later on this afternoon when I get home. Otherwise, I'd like to wish you a fantastic afternoon, and thank you very much for listening. Bye-bye.
Hello, and welcome to this talk on continuous delivery with Azure Web Apps. My name is Vidar Kongsli. I work at Brevid, based in Oslo, Norway. We're going to investigate a lot of the functionality that we have available to us in Azure Web Apps for deployment of software, deployment of our application. And that is a very important part of continuous delivery. So we're going to focus on that. But before we get into the technical details, I would like to point out a couple of things regarding the heritage of continuous delivery. To me, this book, Lean Software Development, has a lot of foundation for continuous delivery. It's a very good book from Mary and Tom Popendick. It was released in 2003, I think. And it has a lot of good information that we can look at. But there are two basic points that I would like to emphasize. First, the notion of delivering software as fast as possible. And the other one is build integrity into our process. These two are to my mind, one of the main topics that we need to keep in mind for continuous delivery. Another book that I would like to point to is the Continuous Delivery book by Jess Humble and Dave Farley, which was released, I think it was in 2010. They give us principles for software delivery that we are going to have a look at. So first, they say that you should create a repeatable, reliable process for releasing your software. You should automate almost everything. You should keep everything in version control. If it hurts, do it more frequently and bring the pain forward. Again, build integrity in. Done means released. We are considering ourselves with everything until our application is in production. And everybody is responsible for the delivery process, meaning that the entire process should be available to all people in the team. And of course, you should do continuous improvement of your deployment system. So, when I started my career as a Lotus Notes development in the late 90s, we had a system where you could deploy your application in a quick, reliable, and repeatable manner. It was all built into the system, and you can create your process around it. Moving ahead 20 years, we have Azure. We have a smørgåsbord, a buffet of different options to choose from, and the problem becomes what to choose. How do we set up our continuous delivery system? And my suggestion is that we should go back to the theory in order to guide us on what to choose, because there are so many options it can be overwhelming. So, what options have we for deploying our software to Azure Web Apps? The first option you are probably familiar with, deploying directly from Visual Studio. It's easily available to everyone. Or you could create your entire build system infrastructure using build servers, for instance, in Azure DevOps Pipelines, or all other third-party solutions such as TeamCity, Octopus Deploy, Jenkins, and so on. But there are more options. One option, which I call version control deployment, is something that we will look into. And also, I will have a look at how we can use the Docker tool and the Docker tool chain to do our deployments using containers. So let's start with Visual Studio deployment. This is typically a build and deployment pipeline for that option. In your local development environment, you code your application, you compile it, you might run some tests, you build the package, and you publish it directly to the web app, to the Azure web app. in the scenario of a build infrastructure, you still have your development, your coding, and you check in your code to the local repository, and then you push it to some Git repository remote. Then on Azure DevOps pipelines, you check it out, it is compiled, you run the tests, you build your packages, and you publish it to a web application. So for the third option, version control deployment, you still do your coding and you check it in to your local Git on your local environment, but then you push it directly to the web app and you have it checked out, you have it built, running tests, build the package, publish it, and run it on the Azure Web Apps infrastructure. So in this case, we don't need any external infrastructure set up for our build and deployment pipeline. So to do this, we use a system called Kudu. It is not this Kudu, but this one. In the Azure Web Portal, you find it under the Advanced Tools. There's also a separate portal that is automatically provisioned that you can where you can access it. And there are a couple of things there that in this tool that I would like to point out. First, on the left, we have a few endpoints that we can use to connect to it using a computer. There is a Git service, there is MS Deploy, there is an FTP service where you can push your application, and there is a custom REST-based API. Also, for the developer, here having a silly glasses, you have this SCM portal, the site configuration portal, or site control management portal, I should say. And of course, you have your normal web front end where your user can access your application. Here, your users have a top hat on for some reason. So what we can do then is that we can, on our local system, do our coding, check it into Git, and then push it directly to the infrastructure and have it built there. So going back to this slide, there are two areas or two paths on the local file system that I would like to point out. One is the repository. Here is where your source code is pushed. And there is the www folder where IIS will serve your application. So the source code is built and then pushed to www root in order to deploy the application. So let's have a demonstration. So here I have a very simple .NET application. It could be other languages, but I choose .NET. So this is just a demo application, .NET Run. This is, as you might see from the naming, Jokes as a Service, or JAS, as I would like to call it. So let's try and issue some requests to it. So here we have just a simple root endpoint where I get some metadata about the other endpoints. I could go to /jokes or /science jokes or Chuck Norris for Chuck Norris jokes. And also there's a health endpoint. So let's have a joke. Okay. I can issue a new request and I get a different joke each time. So this is my important application. I would also like to point out the health endpoint. It is healthy. So what I can do here, I have also provisioned a web application called NDC Oslo 2020 Jokes 1. In Azure, it is empty for the time being, so let's try to push the application to it. So the first thing I need to do is try to enable Git push to it. Azure Web App deployment source config local git. I need the name of the application, NDC Oslo 2020 jokes 1, and the resource group is NDC Oslo 2020 RG. So what I will get back here is the Git endpoint that I can push to. But I need to have some kind of credentials in order to push to it. Azure deployment. Azure web app deployment list publishing profiles. So now I get a JSON array with some usernames and passwords that I can use when I push to this. So here's a username and a password. I will use this to construct the URL. And all the security people look away. This is not how I would like to do it in production, but for the demo purposes, I have a short script here that will construct the URL for it. And then I will register it as a remote for Git. So here I take the URL, Git remote, add jokes, Git push you jokes. So here you might see that it will actually generate a deployment script and run a build and deploy for my application. So it kicks off .NET Publish, basically. Once that has been done, it will be copied to the www root folder, as I talked about earlier. Let's see when it finishes up. It is copying the file, and if we move back here, we shall see that my application is now deployed. Let's have a science joke this time. Okay, good. So the next step that we can do now, instead of having it automatically generating a build script, we can try and create our own script. So let's create a PowerShell script. Sorry, not there. Deploy PS1. No, sorry. So here I basically have a deployment script that is similar to the one that is actually running or being generated automatically. It basically does .NET Publish, and then it uses a tool called kudosync to synchronize the compiled files to www root. So, but what we can do now is we can add some more steps to our build. So for instance, let's run our tests. So .NET test, I need a parameter for that, where I tell it where the test project is. So, and I can try and test my script here locally. Deploy, sorry. Just tell it where to place the files. It will now basically run the tests and then publish the application. Oh, let's see, what did I do? Oh, should probably run the test before, and I should not run this synchronization command because this tool is not available, so I have a separate switch for that. No sync. So now I've added one of the quality assurance steps to my build pipeline, which is running the tests. And before we do anything else, there is also another functionality that I would like to point out that's available to us in Azure Web Apps, and that's something called run from package. Instead of having the application files copied one by one into www root, we are creating a zip archive of our entire application, and then we have the infrastructure mount that into a virtual directory on the file system, which is a more reliable and a quicker way to deploy our application. So if I add a couple of more steps after the publish application, I create a zip file from it, and then I create a separate file called package name txt, which tells the infrastructure which zip file to deploy. So let's try to run that locally first. Deploy temp build tmp and deployment directory publish. So what we have then, what was that all about? Let's see here. I didn't save my file. So in the publish directory, we have one zip file, which is our application, and this package name txt, which only contains the file name of the file to deploy. So before we push this to web apps, we need to tell it to use this deployment method. So Azure Web App config app settings, set settings, a lot of settings. There's a special environment variable that we need to use. Web site run from package. And we set that to 1. Okay, then we can add and check it in. So let's try to push it. So this time, project type run from zip. So what did I do? What did I do wrong here? Project type run from zip. Let's go and have a look at the portal. So here's our run from package. Should be okay. So it said, what does it say? Preparing deployment, skipping build, project type run from zip. So, yeah, of course, there is one thing missing. We didn't tell the web apps infrastructure about our deploy.ps1 file. Good, so that's very important, so let's do that. What we need to do then is create a special file called deployment. And this one should just have one entry, which is the command to run the build from. And here we are saying that it should run PowerShell and execute PowerShell and run this file here. So let's check that in. let's push some jokes. All right, so let's see. So now it says running a custom build command. So now it has started to execute our file. So there are a number of ways we can do this. The first thing it will do, it will look for an environment variable on the infrastructure called deployment. If it doesn't find that, it will look inside the repository root for a .deployment file. And if it doesn't find any of those, it will try to figure out how to build the application, basically. So that was the first approach that we had. So, good. If we now go back here, we can have a look at this Kudu services portal that I talked about, or the SCM. So let's have a look at the file system. First, we can go into the /data/site packages, and here is our built zip file with our application, and the package name txt references which zip file should be mounted. So if we go to the site root, and if we try to edit one of the files here, we will get an error message saying that this is not allowed. So as a consequence of this approach, the web root is read-only, so nothing can write to it because it's just virtually mounted from the zip file. So another step that we can do, or that we can add to our system or deployment system, is to use deployment slots. Deployment slots are virtual sites that you can use to push your applications before putting them into production. So we have basically the same Git possibilities available to us like we have on the main site. So if I run Azure, the web app deployment config source, if I can spell, config local git, and this in this instance I give it the name of a deployment slot that I have already provisioned. Slot pre. I call it pre because it's kind of pre-production. And as you can see now, it has a similar jokes Git endpoint that we can push to. And likewise, we have the same publishing profiles with the same, or rather other usernames and passwords. So I can create a remote for the pre deployment slot. So we can register that as another remote repository in Git. Git remote add pre. And we can also push to that. So basically what we can do now is that we can push the application, have it built on the deployment slot, and then we can, if we want, test that it works. The infrastructure will actually test that the application starts, and then we can switch it automatically into production to avoid downtime. So while this one is building, let's go back to the slides, I think. So to summarize what we have seen so far, we are pushing directly to the infrastructure. We have created a locally runnable build script, which means that we can debug it and run it locally and see that it works. We have added automated testing to our pipeline. We use the run from package feature, which allows to have a more reliable and quicker deployment. And this is approach good for early deployment and for a small team, maybe 1 or 2 developers. So you can extend this, of course, by using a remote repository like GitHub or Azure DevOps repositories. So in that case, you will develop locally on your system. You will push it to GitHub, for instance. Then you might add quality assurance steps like pull requests and pull request reviews. And then you can have GitHub trigger the web application to pull the latest and build it on the build system. So in this way, you can add on branching strategies. You can do different quality assurance like peer reviews, stuff like that. And you can also deploy to different environments, for instance, for different branches in the version control system. So this is also a fairly good solution for small teams, which again does not need an external infrastructure for building or build and deployment. So there are some possible enhancements that you can do. I just showed you the basic steps. For instance, you can have your build system of preference, cake, sake, whatever. You can add your automated site verification steps to it. And of course, you can push to Slack or Teams whenever a deployment has been done. But of course, some of the shortcomings here is that this is not very visible. The history of the deployments to a certain web application it's available, but it's not really easily available. And having reports is somewhat difficult. So let's have a look at the second option, using DevOps pipelines. So just to finish this last demo first, we have now deployed to our deployment slot. We can then swap between production and the pre-production deployment slot. Azure Web App deployment slot swap, slot pre, and here I have to give it the name of the web application, Oslo 2020 jokes 1, and the resource group. So now it will first check that the application is running in the deployment slot. If it is running, then it will shut it down and it will apply the production properties to the pre-deployment slot, and then it will fire up the application. And again, it will check that it runs, and then it will switch traffic to it. Once the traffic has been switched, the old slot will then be have the pre-configuration applied, and then it will be spun up again. So it's it takes a few seconds to perform the application. But okay, let's have our next demo, Azure Pipelines. So let's see here. Let's create a YAML file with the pipeline. Oh. So here I have scaffolded a basic pipeline. There's a trigger which says that it should automatically trigger when you deploy to the NDC Oslo 2020 branch. It will run on Ubuntu. My first step is just to have the build number written to a version txt file so that the application can serve its version number. Then we run the unit tests, basically a .NET CLI test command. Then we publish the test results to the DevOps portal so that we can go through it. Then we publish the application. We zip it like we did on in our build system, and then we publish it to the artifact repository. So, but first, let's try and improve this. Let's first let's try to reuse the script that we already have. So the steps to publish and the steps to run the unit tests. Let's instead run the script that we have, sorry. Pipes. So instead we are running PowerShell deploy.ps1. And also let's add on the deployment part directly. So instead of publishing to the artifact repository, let's just push it directly to Azure. So here we can do a web app deploy. We give it the Azure subscription, the application type, the application name. We use the deployment method read from package like before. And now actually let's, in the interest of time, let's go straight ahead and deploy to a deployment slot instead. Pipes. So here what we added, deployment to the slot name pre, and then we issue a command to switch it into production afterwards. So yes, we have a new file. Git add git. So and this time let's push it to the origin, which is on, oh sorry, origin. Need to use the correct branch. So let's head over to the Azure DevOps portal. Let's create a pipeline. My code is on GitHub. It's this one over here. I'll use an existing pipelines file. Let's have a look on the NDC Oslo 2020 branch. And there it is. And I just go ahead and kick it off. Takes a few seconds to provision the build server. So now it's checking out the code. It's set the version number, and now it's running our custom build script. Good. So while we wait, now let's see. Okay, it's running the tests. We publish the test results. So it picked up our test results. It's deploying to Azure. It's setting this website run from package to 1 before it pushes the package. And now it's finished deploying to the pre-deployment slot, so it's doing the swap. So slots are warmed up. Now it will try to reapply the configuration and start up the application again before doing the switch. So this might take a few seconds. So while we wait, let's just have a summary what we have done so far. So now we have offloaded the build and deployment to our dedicated environment. We can have our build policies set up we can have more advanced pipelines. There are a lot of tasks available on Azure DevOps out of the box, and also through the marketplace that we can add on to our pipeline. But again, there are more moving parts that we need to take care of and need to maintain. And we kind of lose the possibility to test our pipeline locally. Only the reusable test script that we created is really something that we can test locally. So that means that our feedback cycle is quite much longer. When we do a change, we watch the result. It takes a few minutes typically. So let's see how we are doing. So now here, the swap seems to be finished. So if I move to my second jokes server, we should see get some jokes there as well. Good. Excellent. So the next demo that we can have, or change that we can do, is to use the Docker toolchain to build our application and also to deploy our application. So that means that the compile, run test, build package part is inside a Docker file. We will publish the resulting container image to the Docker hub, or rather, I have set up an Azure container registry for this purpose, and then it is pulled from there to the web application. So let's have a look at that as well. So first, let's create a Docker file. So here we have a multi-stage Docker build. So we use two images for this. One is called Slim, or 3.1 Buster Slim, ASP.NET 3.1 Buster Slim, and, which is only the runtime environment. And one called just Buster, which is contains the SDK that we can use to build the application. So the first step is the build step, where we actually restore, we run the .NET tests, and we publish the test results. So here I've done some command line tricks in order to get the test results out. So here, if the .NET tests failed, meaning that it will any tests failed, it will actually create a test failure file. And this file we will pick up in the publish part and stop the publish if there is a test failure. So here, in the publish step, we test, is there a test failure file? Then we just exit with a non-zero error code. Otherwise, we will publish the web application. And basically, we create the final distribution image by copying only the compiled files to it. I would also like to add on a health check, which basically checks that -health is available, so that the application, we can detect early if the application doesn't boot. So Docker build, let's tag it with jokes latest. Here I have already the base image is pulled, so it's quite quick. The restoring of the for the .NET application, however, takes some time often. Now it's running the tests. Good. Let's try and test the container or the image. Let's see, Docker run, access it to port 80, attach jokes latest. So let's see if we can issue a few commands. Okay, so it seems to be up and running. Let's have a science joke this time. Good. So now we have our Docker build pipeline set up. The next thing we need to do is to create a separate Azure pipeline for it. Azure pipelines.docker.yaml. So again, let's have a quick walkthrough. We have a trigger like before. We run on Ubuntu. We create a version txt with the build number. Then we kick off the Docker build, basically the same command like I just tested locally. And then we have a separate step to fire up a container from the image which is labeled test equals true. And here we copy the test run results. And then we remove the container before going on to publishing these test results to the Azure DevOps. So this is kind of a way to extract the test results from the image. So the next thing, we log into the Azure Container Registry. We push the container image there, and then we tell the web application that it should run this container, or should use this image to and create a container from it. So here we use the Azure CLI to set Docker custom image name. And again, we do this on a deployment slot, and then we swap it into production. And this time I used Azure CLI also to do the swap operation. So again, let's check this in. Let's see, do we have everything? We have a new Docker file, and we have the Azure pipelines for Docker. Oh, let's do one more thing. Let's just go, and we don't need the old pipeline to trigger anymore. So let's just change. Let's change this. So it is pushed. Then we move over to the pipelines, Azure DevOps pipelines, and we create a new pipeline. So, sorry. New pipeline. Again, GitHub. Existing pipelines file. Let's look at the NDC Oslo 2020 branch. This time, let's have the Docker one and kick off a build. Okay, so now it's kicked off the Docker build. It has pulled the images. It's starting running the script. Okay, so it's running the tests. Tests are good. And publish the application, or sorry, publish the image to the repository, push the image. And we tell the web application which container or which image it should use. So, of course, here in this case, I have a provisioned a web application which runs on a Linux application plan. That's basically it. It also has set a few configuration parameters. Because I'm not using the Docker hub, but rather I use Azure Container Registry, I need to have the URL to the server and a username and password that the application can use to connect to it. Yeah. So let's see, how are we doing? So it has deployed the container. It's now doing the swap. So let's see if we can issue a command or issue a request to it. So the host is, this is jokes number 5. Let's see. Oh yeah, there it is ready. Serving jokes. Let's have a Chuck Norris joke. Good, there we go, there we go. So also I would like to point out that we now here in the portal can go and look at our test results. Basically we have everything available to us here. Also in the case where any tests fail, we can go here into the portal and see which tests failed and so on. Good, so just a summary. To summarize, we have now used the Docker tool chain, which might be your preference. You can easily develop, you can run and debug everything locally, and everything like the runtime in tools included in the container image, so that you are basically free to pretty much include anything that can run on Linux and can talk HTTP to run your service. You get a somewhat cheaper hosting if you move to Linux versus Windows, and further down the line, if you want to change hosting provider, you have an image technology that can run on all large providers. So just to have a brief talk about the key features of the Azure Web Apps that do a web application service that we have talked about. We have seen how we can run our build on the Azure App Service itself. We have seen how we can use deployment slots to deploy with 0 downtime. You can also do an automatic swap on Windows infrastructure if we want to, because in my examples I explicitly issued a swap command, but you can have the infrastructure set up to do that automatically once a deployment is done in a certain slot and it detects that the application is healthy, it can swap automatically into production. We have also looked at the opportunity to run containers on Azure Web Apps. I didn't say much about that in the beginning, but I have provisioned all the infrastructure using ARM templates. I would urge you to do either that using ARM templates or the Azure CLI, any form of scripting instead of manual provisioning is good. So again, we started out to look at the different options that we have for deployment to Azure Web Apps. And I said that we try to use the principles of continuous delivery to guide us on how to choose how to do it. My message would be that you should choose the deployment approach based on your current needs, and also be open to switch approach during the lifetime of your application. But have your build and deployment scripts checked into VCS. Have it in the proximity with your code so that it is available to developers in an easy manner. And also you can reuse it if you switch your deployment approach. So here are just a small summary. Pushing from local Git is a good way to get started. Maybe for development, small scale development, single developer, maybe 2 or so. As a proof of concept, doing prototyping, it's a good approach. You can add on to do the deployment via GitHub, for instance, or services like that. For small teams, you can have multiple environments. You can do branching, creating your logic and your process around that, pull requests and so on. The Azure DevOps pipelines is of course a more full-blown dedicated infrastructure for complex solutions, more advanced workflows, versioning, reporting, and so on. And also as a variant of that, you can combine that with the Docker tool chain, where you are kind of more cloud independent. You can also have versioning, reporting, and so on. So it's more of a what you prefer in terms of your CI/CD. So that's it. My final message would be to travel light. Do not carry more than you need. Don't have too much luggage. Rather, just pack whatever you need. So with that, I would like to thank you very much for attending. I will be available on Slack if you have any questions. So let's have a look. Okay, no questions there now. But again, thank you very much. I'll be happy to answer any questions if you have any. Thank you.
Hello, everybody, and welcome to Room 1 at NDC Oslo in virtual. My name's Layla Porter. This session is TDD and the Terminator, an introduction to test-driven development. Now, just a quick note, this is an introduction to TDD. If you are already a TDD whiz kid, you may want to pop over to any of the other amazing talks happening right now. You've still got plenty of time if an introduction to test-driven development isn't for you. But if it is, then let's begin. So, as I said, my name's Layla Porter. Welcome to my home office. I am a Microsoft MVP. I organise my local .NET user group here in Milton Keynes, which is about 60 miles north of London. I love C# and I am a senior developer evangelist at Twilio. So if you've not heard of Twilio, we're just a cloud communications platform. So feel free to find me on Slack and ask me some questions about it if you wish. But you're probably asking yourself this question right now. Why TDD and the Terminator? And that's a very good question. And to answer that, I need to take you back to a previous job of mine. It was quite a while ago now. And this was also at a communications company, and my team worked on a cloud platform that allowed carriers to manage communications and their rating and routing of telephony. So it's quite a complicated system. So we worked on the platform that allowed them to manage it. And we relied solely on a team of 6 testers. And by that, I mean we didn't have a single unit test, not one. No integration tests, nothing. We just about had UAT testing, which is user acceptance testing, but everything was based on this team of 6 testers. That worked out fine for me for a while. And then after one particular release, and our release cycles were sort of once a year, we got to the point where we had 9 weeks of regression bug fixing. So just let that sink in. 9 weeks of development, which was only fixing regression bugs. It was a bad time. And at this bad time, I thought there had to be a better way of doing things. Surely this couldn't be the way that quality software was written. And that's when I started to research different ways of doing things. And I came across TDD, or test-driven development. And I was like, yeah, this sounds right up my street. Definitely something I would like to watch. Oh, and I've just remembered, if you're watching on YouTube, you can also watch on WebEx. Just remembered I was asked to say that, and it just popped into my head. So this is also on WebEx, so feel free to watch on there as well. But anyway, back to TDD. So I thought this is a much better way of doing things. I'm going to learn how to do TDD. Or more to the point, I'm going to attempt to learn, because that's what it was. I didn't know where to start. I didn't find TDD very accessible. I felt the learning curve was really steep. I tried reading books. That didn't help. I tried watching YouTube videos, and it was like magic happening on screen. I also watched Pluralsight, and nothing really helped. And I was like, ugh, I need something simple that I can build myself that will help me relate to the issue. And that's what I did. I'm a fan of the Terminator movies, so I created my own little tiny TDD Terminator app. And I have rewritten that and revamped it a little bit, and I'm going to share it with you in the aims that if you're stuck on how to get started with TDD, or it just doesn't sink in, that this may help you, just as it did me. So let's have a look at some TDD successes. And the first one of those is acceptance criteria. Now, this is where you speak to the project or product owner or your project manager, and you really get them to define what the requirements for each feature are. And what does this mean, really? Well, it means that you don't have any wishy-washy requirements and you know exactly what your code should do. And if you know exactly what your code should do, then it's very easy to write tests for it. And so that's the first thing. And this means that you have a greater understanding of what your code should do. And once you've written your code, you're not going to have your product manager or product owner come up to you and say, well, I didn't mean for it to do that. I actually meant for it to do X, Y, and Z. So you save time and everybody has a clear understanding of what should be happening. So the next one, focus. Now, as developers, we are prone to ADHD, and there's a term called shaving the yak, and I've got the link to a good blog post on it at the end of the talk, so don't feel like you have to rush off and Google it now. Well, of course you could, but the phrase shaving the yak, and once you know what it means, you'll be like, yes, that's exactly what I do. And what a lot of us do is, right, I need to implement this feature, but hang on, to implement this feature, I need to write this bit of code. Oh, but to write this bit of code, I need to update the database, and so on and so forth. And you just get on this endless to-do list, and you never actually get to do the thing that you really wanted to do. So focus, and this means that you have distinct pieces of code, functionality, let's call it, and you know exactly what you need to do to complete this little test. So you write a test or a collection of tests and you say, oh, okay, if I fulfill this bit of code, that's it. I keep focused. All I have to do is write some code that fulfills this function and passes this test. So you don't go off anywhere else and looking at other things. You keep your focus. So that's really helpful. So the next thing we have is interfaces. And you may be thinking, well, what's that got to do with TDD? Now, I'm a practical person, so I have a very pragmatic approach to TDD rather than dogmatic. And a lot of people you'll see will be like, no, you just write the bare minimum of code. I like to write interfaces for my TDD. They're a coding contract. And when I'm working in a team, I can actually say to Clara, my teammate, here's my interface. This is what I expect my code to fulfill. And if you need to get on with your code, this is what my code will fulfill, even though you haven't written any of the functionality or the implementation of that interface, because you've written your tests and you know that your tests are going to fulfill that interface. Okay. So this leads on to a really useful aspect of TDD. And that's asynchronous development. And that means that I am not dependent on Bob, who's working on a particular feature, to finish his feature before I can start working on mine. Now, at the old company where I used to work, we couldn't go and just pick something out the backlog. It was really, oh, well, actually, that needs this story to be finished first, and oh, I need to make sure that that's changed and that's implemented. So you're constantly picking through the backlog and seeing what you actually can do, rather than just grabbing one that fits your time frame and your interest or your skill set and getting on with it. So having interfaces and proper small pieces of code and all of the above will help you be an asynchronous development team. And because you're focused and you have coding contracts, you have cleaner code because you're only writing enough code to pass a test. You're not going off and shaving that yak and doing everything else that you think you need to do. You are simply writing enough code to pass the test. So you don't get bloat or unnecessary code or code where it shouldn't be. You just get lovely, clean code. This one is one of my favorites, safe refactoring. Now, remember those 9 weeks of fixing regression bugs? I wouldn't have had it if we had tests, because if as soon as you regress your code, your tests don't pass. So you get an idea straight away that you have made a regression bug, and you don't have to wait till release day to find out that by working in a particular area, you've broken a whole nother area. So safe refactoring is a massive factor for tests. And I will just put that caveat in. Some of these things are not just restricted to test-driven development, but unit testing in general. So just having unit tests allows you to have safe refactoring. So that definitely leads on to fewer bugs, which everybody loves, fewer bugs. And of course, if you have fewer bugs, you're spending less time fixing bugs and more time implementing new features and developing a better product. So you get increasing returns, which makes everybody happy. And the final point I'm going to raise is living documentation. Now, tests are not a replacement for documentation. However, they are a really good start. If you have a new developer join your team, if they go and read all of your tests, which should have descriptive names, they can understand what your code is meant to do. You can also build your actual documentation from your tests. So it really helps in so many different ways having tests. Okay, excuse me. So let's go back to the Terminator and have a look at how we apply some of these things to our Terminator app. And the very first thing we want to look at is the process. And what is the first thing in our process? Well, that's gathering the requirements. Let's have a look at how we're going to gather our requirements for our Terminator app. Okay, so we have a boy on a motorbike and we're having a look at him, we're investigating him further, and we've actually identified him positively as John Connor, and we really need to investigate John Connor further because he's a target. So from that, we can derive a couple of requirements. And the first one is scan subjects and determine if they require further investigation. And the second one is investigate subjects of interest and determine if they are indeed the target, and then terminate them. We're going to focus on the top one, scan subjects and determine if they require further investigation. So that seems like a really nice requirement to start with, nice and succinct as well. So what we need to do now is start with failing tests. And these failing tests mean that you haven't got any code written because you can't pass tests if there's no code. So it's a really good start to test-driven development. And this is important. When you write tests after coding, you may be writing them to fit your code and not your requirements. And what I mean by this is, imagine you've written an API endpoint and it returns 200 and content. And then you go and write a test that tests to see if your code returns 200 and some content. Your tests pass, everything you think is hunky-dory. But actually, when you go and look at the documentation, it's not meant to return 200 and content, it's just supposed to return a 204. And your tests have passed, and anything you change will fail your test. So, you think everything is okay, but it doesn't actually fit your requirements. So unless you're cross-checking your tests with your requirements, you could be writing them to fit your code. Now, if you write your tests first, the only thing you've got to go on is the requirements. So you would look at your requirements, go, right, this has to return a 204, and you write the tests to check that it's returning a 204. So that's a really valid reason for doing TDD. Okay, I like to use the red-green refactor pattern, and what that means is we write a failing test and we write enough code to get the test to pass. So the failing test is red. When your test passed, it goes green, and then we can refactor. And that's a really nice iterative process that you can keep doing. And we're going to go over to code and have a look at what that looks like. So let's go this way. And here I have a simple application. This is just built off a template. It's nothing fancy. And I do have the GitHub repo for this as well, which you can have the links at the end of the talk. I will just say I'm not checking Slack or anything. If you have questions, please just save them for the end, and there'll be time at the end for me to go through and answer them. So let's have a look at what I've got in this code. The first thing we're going to look at is this interface called iSubject, and this has one property called subject name. I have an implementation of that called subject, pretty straightforward. And then I have an iSubject analyzer. Now, if you remember, our requirement was, should we go and investigate a person further? So we've got this being a bool, yes or no, and investigate further. And we're going to pass them in a subject. And over here, we have our test class. Now, I use NUnit in this particular instance. I like NUnit. You could use XUnit, and there are many arguments for using XUnit because it's more maintained and it's more modern. You can, of course, use the Microsoft testing framework as well. I've used all of them. I just happen to like NUnit, and I've put this one in here. XUnit is very similar, just slightly different decorators, but they all do roughly the same thing. So what we have is test fixture here is part of NUnit, and it's saying this is going to be a test class. And once we go in here, you'll see I have this private of iSubject analyzer. So that's this interface here, and I've called that SUT, and that stands for subject under test. Calling the class that you're testing something such as SUT differentiates it from many other dependencies. So perhaps this class, subject analyzer, is dependent on multiple classes. If I have all of those in here, because I'll need them, and they've all got their class names, by calling this SUT, it just keeps it clear that this is the class that I'm testing. So it's just makes life easier. Next, we have this setup, and this is where I can set anything up that I want to use throughout all of my test methods. You can set stuff up in each test method, but if it's something you're going to be using again and again, it's nice to set it up at the beginning. And this is where the frameworks differ slightly. I particularly like this way of doing it with NUnit. So what we need to do is actually create an instance of SUT. So we'll come here, SUT is equal to new, and I don't have an implementation of iSubject analyzer. So all right, we need to create one of those. So let's come over here to services, and I'm going to add one in here. So we'll have a new file, and we'll call that, we won't have a new file, we'll have a new class. And we're going to call that subject analyzer. I often get asked what IDE I'm using. I'm using JetBrains Rider. I happen to like this. As you may have noticed, I'm on a Mac, and I find it's really good for development on a Mac. It's very similar to Visual Studio with ReSharper on. I like the testing framework from ReSharper as well, so I just happen to use it, but it doesn't make any difference to what we're doing. So I've now got this class called Subject Analyzer, and it implements iSubject Analyzer, but it doesn't really implement it because we haven't said implement missing members. So what we do when we get an implemented interface is we'll get something that looks like this. And it says, throw new system not implemented exception. And that's absolutely fine. We don't need to change any code yet because we haven't written a test yet. So leave it like this. Let me zoom in a little bit for you. And let's go back to our tests. So now that we've got the implementation, I can go new subject analyzer. And this is now ready for us to use and test. So down here, I've got our requirements, scan subjects and determine if they require further investigation. And so let's go and write our first test. And that's going to be a public void. And what we're going to say is Terminator should determine to investigate. Well, let's go look for Sarah Connor. Let's have investigate woman further. Okay, so just a note on naming of your test methods. Many people will delimit each word like so with an underscore. I find that harder, but you may prefer it. But what I like to do is have what we're doing, what the thing is, what it should do, and then sort of the end part. So I like to divide it up into 3 parts, and you'll see as I name more methods what that looks like. And what we need to do is make this discoverable to our testing framework. So this is with another decorator, and this is called test. And you can see now I've got this little play button here, and you can see it's going to run my tests, and we'll get to that in a moment. So there's a few things that we need to think about when we write a test, and that is we need to arrange, we need to act, and then we need to assert. And so the action is going to be actually the test method. So that is going to be var result is equal to SUT dot investigate further. And you can see that we've got a red squiggle here, which means we need something in here, and that's going to go into our arranged. If we go look here, it wants a subject. So let's create a subject. Var subject is equal to a new subject, and let's initialize it here as well and bring in the missing usings, and that has a subject name, and let's call that woman, because we're going to look for a woman as it says up here in our test method. And now we can pass that subject in. And I happen to know that if we're looking for people to investigate further, because we're looking for Sarah Connor, we need to investigate a woman we see further in case she's Sarah Connor. So then we want to go result dot. I use fluent assertions, so that's going to be should be true. And I quite like fluent assertions because they're nice and readable. Let's bring that up a little bit. But you don't have to. You can use the built-in assertions that we're going to have a look at in a little bit. We'll use one of those. So result dot should be true. So very quickly, someone can come along and go, Terminator should determine to investigate woman further, and we can see what this is. So let's go and run our test. Now, I'm going to run them from up here first because it's the first time we're doing them, and I want it to go through. And of course, it wants to do that because I clicked run rather than tests. Run unit tests. So we've now got our testing window up here. And you can see everything's red. So we've got our red part of our red-green refactor, which is perfect. And you can see here, it's looking at the classes. If I had more classes, they'd all be listed here. And then inside the individual methods. And it tells you what's wrong. If I move that across, you can see that it says it's not implemented, which is exactly what we would expect. So let's go back to our class and remember our number 1 rule. We only want to implement enough code to get our test to pass. Now, as I said, I can't see Slack, but feel free to all scream it out in Slack if you know the answer. And so the simplest thing we can write here to get the test to pass is return true. And that was a massive aha moment to me, okay? I was like, that can't be right. But if we come back now, and if I run all the tests down here, we'll let that do its thing, green. And that was like an amazing aha moment for me, that I just write return true, and that's the start of TDD. So let's get on. So let me zoom out a little bit here. We're going to go and write another method. Let's think about if we see a T1000. I'm sorry if you're not into the Terminator movies, you're going to get a lot of jargon that you might not understand. So if we see a T1000, let's think we're in Terminator 1 now. We're hunting John and Sarah Connor. So is a T1000. I know I've munged the movies together, but forgive me. And we're not interested in them because they're on the same side as us. So let's have a look. Terminator should determine not to investigate further. And I'm not worried what this particular thing is. We're going to say T1000. Pass that in, and now we're just going to update this to be false because we're not interested in investigating a T1000. All right, let's run our code. Actually, if I run them all, we can have a look at what we've got down here. You can see it's already discovered that second test, and that one's failed. So let's go and write just enough code to get our test to pass. So let's come back in here. What I'm going to do is just cut that, and if subject name is equal to woman, or a lovely bit of string matching here, we'll return true, otherwise we'll return false. And I will just say that I hope nobody ever programs a terminator by string matching, okay? We're not going to do that. But it works for demonstration purposes. So now we've got this, let's run our tests again. Boom, they're all green. You're liking this. Let's go back over here. So now we've seen John Connor. So that's a boy we want to investigate further. So I could go and copy this whole method again and paste it and do it, but it's going to get a little bit tedious. So what we're going to do is update this method to take multiple test cases. So let's start by renaming it. Who should we investigate further? And we're going to change this decorator to be a test case. And in here, we're going to say a woman. And we can add as many test cases as we want to here. And you can have loads of them. And immediately, if you notice down here in our Test Explorer, I've now got this set of sub-tests under this one, Terminator should determine to investigate further. So we've got two tests in there, boy and woman. We've not run those tests yet, so they've got question marks. And how we get those in is we add them as arguments. So string, and we'll call this one subject name. And then what we need to do is just where we've got woman down here, we'll just say that subject name is equal to subject name. And these are all going to be true, okay? And we'll come to how we can update this further back in slides. So let's go and run all of our tests. And you can see the one for boy has failed. So let's go back. Now you're probably going, oh, why didn't you just do the switch statement here or something? But that would break our rules. We're only writing enough code to pass our tests. So I'm just going to do a really lovely, and this is gorgeous, isn't it, folks? Don't worry, we will refactor. So that, let's run. It's just enough code to get my tests to pass, hopefully. And there. So you can see really clearly how we've quickly started to build up code. I'm not saying that this is particularly nice code, but we've got two tests and we've written our code. So let's now go back to the slides and see what we can do further. So I want to go this way and let's continue. So now that we've got the basics in there and we've got our tests, we can start to safely refactor. And this is really key. And let's go and have a look at what we've got. So imagine now I've added in tests for a girl and a man. We want to go and investigate them all. So here's my lovely stack of if statements. And I've gone and made a switch, not a fancy new C#8 switch, just a plain old basic switch. So we safely refactored that. And if we have a look at our test class here, you can see that I've got all of those test cases stacked. Okay, so that all works. And if I look at my bottom class there, the Terminator should determine not to investigate further. That's fine too. But now, requirement change. Let's see what this one is. Okay, so Sarah Connor's doing something funny with the Terminator's head. This is interesting. And it looks like he can learn things. Now, if you have not seen the director's cut of Terminator 2, this will be an unfamiliar scene to you. This is only in the director's cut, and a little bit of trivia there is the head you see in the foreground, the back of the head is Arnold Schwarzenegger's stunt double, and the arm is Linda Hamilton's sister. So this hand closest to us is Linda Hamilton's sister. So just a little bit of movie trivia there. So they switched his chip from read only so he can learn things. So our new requirements are protect John and Sarah Connor from threats and an ability to learn. So let's go back and have a look at our code. So this all still looks fine. We've got a nice success. It's green. But we've got Terminator should determine not to investigate further. But now we want to, because if we see a T-1000, they're a potential threat to John and Sarah. So we need to investigate them further. So if we update our switch and say, yes, we want to investigate T-1000, we get this error, expected result to be false, but found true. So now what am I faced with doing? Well, I'd have to go and modify my tests. But I don't want to. So we should design applications to be more robust. Because we shouldn't have to go in there and fiddle with things as soon as a requirement changes. That's tedious, and that's not why we have all this safe refactoring and things. And to make software more robust, you can look at design patterns. Now, anyone who has known me for a while will know that my Twitter bio used to say, so solid. Okay, at the moment I am championing Black Lives Matter, so I have that on my Twitter bio at the moment, but previously I had so solid because I am a big advocate for solid. But this isn't going to turn into a solid talk, so never fear. We're going to have a look at them briefly though. So in case you don't know what solid is, here it is. It's the single responsibility principle, the open-close principle, the Liskov substitution principle, the interface segregation principle, and the dependency inversion principle. Now, we've already done some of these, and we'll cover that in a moment, but we're really interested in the top three, SOL, or the sunny side, as I like to call it. Let's look at these closer. So the single responsibility means that every class or module in a program should have a responsibility for just a single piece of that program's functionality. Now, if you think about that from our requirements, if you've got multiple things happening in a class, multiple pieces of functionality, how do you test that? How do you know which is the failing piece of this big method? If I take you back to the company I used to work for, we had controllers with a controller method in there that was 800 lines of code. And it had so much functionality going on there. You wouldn't even know where to start to debug that. We had breakpoints galore everywhere. It was a nightmare. I wouldn't inflict it on my enemies. Or maybe I would. But anyway, so this is really key principle that you just have that single piece of functionality. And on to open close principle. Software entities such as classes, modules, functions, etc. should be open for extension, but closed for modification. What does that mean? When I first saw this, I was like, I don't understand. I don't get it. How can it be open for extension but closed for modification? I don't get it. Well, I'm going to show you in a moment a sort of example of how this works that can be amazing for keeping your code in a really good functional way that you don't have to go and rewrite your tests or anything. Okay, and we're going to do it in a moment. And the final one we're looking at is the Liskov substitution principle. Objects should be replaceable with instances of their subtypes without altering the correctness of that program. And that's going to be key for what we're going to do in a moment. We've already seen that we can have multiple implementations of a certain interface, and the tests should all still work similarly. So let's see this in action. We'll come over and refactor our code. Alrighty. So this is what we've got. We've got our terminator should determine to investigate further, and we've got the 4 test cases. And then we have the one for the T1000 rather. So I am going to rewrite those 2 tests into this one test on the right-hand side. So what we've done now is we've added some more arguments, and let's step through. So let's take that first decorator test case, and we've got woman and true, and they map to those 2 arguments, string, subject name, and bool outcome. And then the subject name works just the same. We pass that into our new subject, and then the outcome is in our result. So this is now not fluent assertions. We're going into the regular assertions, and result dot equals the outcome. Okay. So you can see there that we've actually got the test case with the T1000. We're no longer going to investigate the girl or the man. We can put whatever we like in here and as many test cases as we want, and they should all work in the code in the same way. And as you can see, they do. So we've got all of those passing based on our current code. So let's go and have a closer look at how we can refactor this code even further. So let's see what we've got at the moment. We have our public bool method called investigate further that takes a subject, and that currently has that rather delightful switch. We have our iSubject, and we have our implementation of iSubject. And what I'm proposing we add is this. Now this interface down here in the bottom right is called iSubject rule. We're going to create a rule set, and we can do all of this because we've got our lovely tests in there first. And this has 2 methods, isMatch. So does this rule match the subject name coming in? And then if it does, is this subject of interest? So let's now have a look at how we write those rules based on our code. So on the left, we have our current code with the switch, and on the right, we have our first implementation of an iSubject rule, and that's the isWoman rule. If we look at our switch, we can say that if there's a woman, is it of interest? And you can see, yes, it is. We'll return true. And then we've got the isMatch method, which will take the subject, and using a little bit of very dodgy link here, it's going to have a look and see if that matches. Now, of course, I know that if you had a man rule and you pass woman, yes, woman contains man, and it gets messy, but just forget that. This rule could be anything. You could be heading on over to cognitive services and getting a certainty back from them on whether a subject is a woman, and based on that certainty going and investigating. It doesn't matter what this isMatch is, it's going to work the same way. So we're just going to use string matching here. Do not build a terminator by matching on strings, please don't. But it's good for demonstration purposes. So now we have an isDog rule, and dogs are lovely, and so we don't need to investigate them further. So you can see that our of interest method is going to return false here. Okay, so we can go and pull out as many rules as you like, and they all have to implement iSubject rule. That is the key. So I've got the investigate further method on the left, and I have it on the right now, but you can see I've added some more code to my subject analyzer class. And we're going to step through this because you're thinking, wow, that switch just looks lovely now. Can we not go back to the switch? No, we can't. We're going to go through and have a look at how we can refactor our code to be much more extensible. So I'm going to bring up those rules on the left, and let's start to step through our code and with those in mind. So the first and most important thing we've added is this collection of iSubject rules, and we've just called that _subject rules. And it's very important that this is iSubject rules, because now we can have any implementation of iSubject rule added to this collection, which is what we do in the constructor. So we've now got a constructor. We have we've instantiated subject rules, and you can see that's a new list of iSubject rule, and now we can add our women rule and our dog rule. So here is where you can do your extension or your extensibility. We can just keep adding new rules. Okay. And we'll show you that in a moment. So let's go down and look at our investigate further method. The signature is exactly the same, so our tests should work exactly the same. So we take that subject in, and the first thing we're going to look at is we're going to get a rule. Out of our collection of rules, we want to pluck the relevant rule out. So we use a little bit of a link here, and we use an expression to access our isMatch rule from our for example, is woman rule on the left, and we pass in our subject, and that will either return true or false. And if it's true, we're going to pluck that out, and now we've got our rule. So say our subject is a woman, we pass that into the investigate further. That rule is going to be true, and we get that is woman rule. And then we pass that rule into our investigate further our investigate method. Now that's a private method, and we'll have a note on private methods in a moment. So we pass that rule in, and then we can straight away call the of interest, and that will tell us whether it's true or false. And that means investigate further will return true or false. So we've tidied that up very easily without a big switch. Now, think if we did use a switch and we had loads more things that we needed to investigate, that switch is going to get bigger and bigger and bigger and bigger and bigger, and we don't want that. We've already seen it grow from 2 to 4 and so on. So we definitely, this makes it a lot easier. But back to private methods. If you need to make a private method public in order to test it, then it's time to refactor. Now, imagine we're working asynchronously, and I have been given an interface by Clara. Clara has implemented all of her stuff using that interface, and everything's going great. And I go, well, I really need to test this private method here that I need. So I'm going to add it to the interface so I can test it. But I've just broken all of Clara's code, and she's like, well, I don't need this, so I'm not going to do an implementation. So she just leaves it as throw new not implemented exception. Now I have seen classes that have 20 or 30 of these methods with throw new not implemented exception. And that's a real code smell. It's unnecessary code bloat. Now all your tests, well, you can't write tests for this because, well, they're not doing anything. They're all going to fail. So this is really not great. Now, if I do want to make my private method public, I should write a second interface for it, which brings me on to the I in Solid, the interface segregation principle. And this splits interfaces that are very large into smaller and more specific ones, so that implementations will only have to know about the methods that are of interest to them. So now I can implement 2 interfaces on my class, but Clara just needs to implement the one. And we share that one, but the additional stuff that I need, I just make a separate interface for it. And so that's a really tidy way of being able to look after your code and keep it clean and minimalistic. So let's have a look at our code now. So we've implemented this change. You can see we've got that collection in our constructor, And then down here, we've got our public method, the investigate further, and we've got our investigate private method. And now when we pass in those two rules, test those test cases, dog and woman, we get it all passing. Now, as I said, this is extensible. It fulfills the open-close principle. So it's open to extension, but closed to modification. As I get new rules, all I have to do is add them to the collection. My code in Investigate Further doesn't need to change. It's closed for modification. We're not modifying that any further, but I can keep adding new functionality by adding new rules. And you may be thinking, where do I use this? Well, I've recently did this for a notification handler. So you could have notification rules based on different criteria, what type of notification is sent. So you don't need to go through an if statements, you just have a rule and it will go through. So it's a really good way of making code totally extensible. And with that, good practices and code management becomes infinitely easier. So you don't need to worry about refactoring tests and refactoring your methods. You can just extend till your heart's content. So that's fantastic. So let's have a look at TDD failures. And this is specifically through the learning of TDD and implementations and things. And the biggest one is underestimating the learning curve. So if you think that you can pick up TDD in a day, maybe you can, but a lot of people are going to be going, I don't know how to start. And so underestimating that learning curve can be a real issue. And it can be really disheartening as well if you think, am I being really stupid here? Is that surely this is easy? It's not. It's a complete cultural change, a massive change to the way you think as well. Many people confuse TDD with unit testing. So I've done Twitter polls and asked people, well, do you do TDD? And they're like, yeah, well, I write my code and then I write my unit test. I'm like, no, that's just testing. It's not TDD. TDD is specifically writing those failing tests before you write a single line of code. And another failing is thinking TDD is enough testing. So my previous job, we were all TDD, but we only had TDD with unit testing. We didn't have integration tests. We didn't have a testing team. We didn't have UAT testing. So we just depended wholly on unit tests and TDD. And I'm sure you've seen enough memes about unit test versus integration test. Not starting with failing tests. That's a code smell. If your tests immediately pass, then you know you probably haven't written your test first, because how is your test going to pass if you've not written your code? And then not refactoring enough, being lazy and not making that private method public and tacking it onto Clara's interface and screwing over her code. You don't want to over-engineer, but you want to make stuff refactored enough to be maintainable. And obviously, if something's going to be changed again and again, or hopefully with the scope. And basically, the rule is you can refactor something once. And if you come to refactor it a second time, then you should be thinking about what you should do to make it more maintainable, okay? And not actually doing TDD. I'm really, when I started, I was really falling foul of this one. So remember, we had that switch and I said, just return true. Well, I wouldn't just return true. I'd be like, oh, well, I need a switch here. So I'd write my big switch and I'd be like, oh, look, my test passed. And then I'd be like, right, what's my next test? So I'd write another test. Oh, it passed. Oh, I've already written my code. So I'm not actually doing TDD anymore. I'm writing unit tests after the fact. So you have to be quite strict when you do TDD. And, that's difficult. So let's have a look at implementation within your organization. It can be controversial and is a significant cultural change. So you may, when you implement it, you may start to really slow down on your output. And your product manager is going to be like, what's going on? Why is this all changing? So that can lead to an initial drop in productivity, which is my next point. But it can be controversial. Not everyone is going to be on board. So you need to be kind and patient and help people make the cultural change. And it may be that people just don't want to do TDD, certain members of the team, and be prepared that they're going to move on, because it's not for everybody. Be sort of open-minded about things. So as I said, it can give an initial drop in productivity, and that can be really disconcerting. If you've got a high performing team and suddenly you've halved the number of stories in their sprint, you haven't halved it yet, you've got the same number of things and they're now not finishing everything in the sprint, that can be disconcerting. They're like, why are we so down on all of this? Why are we not progressing still? So, you really need to be mindful that this could be a really disconcerting time for your developers. But if you stick with it and you get past this this drop in productivity, and you speak to your product manager and tell them what's happening, you will get a productivity increase. It will go up and your reworks will be reduced. So you'll get less bugs and you'll get faster and faster and faster. You have to be prepared for that initial slump and reduction in productivity. But once you're going, the productivity just skyrockets because you're not creating all those bugs. So you get an increased understanding of requirements and their acceptance criteria. So your relationship with the product manager or the product owner becomes far better because you're saying, no, I haven't got enough information here to write the code. So you're putting the onus on them to go and really think about how the product should work, what they need, and then coming back to you and going, this is what it should do. So everybody has a greater understanding. So you won't get those bugs where you say, well, this didn't do what I wanted it to do. So basically, if you take one thing away from this talk, well, let's say two. Let's go back here and think about the implementation. I just want to say, be kind and patient. That's a really big thing, okay? Be kind and patient. It's a big cultural change, and don't expect it to happen overnight. And just communicate with everybody, and that should go much better for you. So on to the, if you take one thing away from this talk, and this is going back to my big aha moment, and that's if you have code that looks like this, you want to return true. Write the least amount of code to get your test to pass. And if that means return true, just return true, okay? Don't be afraid to do it. This blew my mind. Every time I've given this talk, someone has come up to me and said, that was either their aha moment when they learnt TDD, or it was their aha moment within this talk. So I hope that that has helped some of you understand TDD a little bit more. And with that, I want to say a huge thank you to all of you for joining me, to every one of the organizers, to my host in the room, and making what is a massive conference that I've been to the last few years in Oslo, and taking it onto a super interactive event online. So a massive thank you to everybody. So here are some things about me. You can follow me on Twitter, Layla Codes It. This repo you can get on that bit.ly link, TDD Terminator, or you can find it on my GitHub where it's Layla-P. This deck is available on that link there. I am on Twitch. I'm part of the Live Coders team. So you can watch me on Twitch, where I predominantly talk about Azure Functions on a Monday and General C# on a Thursday. I will be adding in some more scheduling as well in the coming weeks. So feel free to catch me on Twitch. And as I promised, if you want to know more about shading the yak, you can check out that link. So awesome. Right, I'm going to stop sharing and bring up Slack on my machine. So if you want to post any questions in there, feel free to ask me. Let me come back now over to Slack. So
Welcome to this last session of NDC Oslo. I am fully aware that I am the only thing in between you and your weekend, but I'll try to make that journey as nice as possible. Now, my name is Markus Degi, and I work as a software developer for Equinor in a team consisting of 13 developers developing scientific computing software. And we develop many different applications, one being what you could consider a legacy application. Now, I could also talk about our more shiny and new projects, but to be honest, I think some of the most interesting problems that we face, both with respect to computer science, but also with respect to development methodology, comes from this legacy projects. So because of that, I am here today to give you this talk named Strangling Hydra One Head at a Time. Now, to give you a bit of context, I am going to tell you the story of Acht. Now, if you were hoping for it being a Hydra, then I have to disappoint you. And I think you would have to try to find a movie instead later tonight to give you that. But dealing with legacy software, it can sometimes feel like you're chopping one head off and two new comes up. But that's a different story. It is also not about peace. So for the non-Norwegian part of the audience, I can tell you that Acht is the Norwegian word for peace, which means that now you got to learn a little bit of Norwegian culture, even though you didn't get to go to Oslo. Now, Acht is an acronym for Ensemble-Based Reservoir Tool, and it was created as a tool to reason about the uncertainty in reservoir models. Because in Equinor, we are producing oil and gas from reservoirs, and the honest truth is that no one has ever gone down and inspected these reservoirs. So we have some idea about what they look like, but we don't know for sure. So it could be that it looks like this. It could also be that it looks like this. And it could be that it looks like this. There are various properties about a reservoir that is interesting. It can be how well fluid moves through the reservoir. It can also be what the reservoir itself actually consists of. So normally there is some water at the bottom, and then there might be oil and gas above. And as you might imagine, we do very much care where that line goes. And it might be like this, it might also be like this. And that is key information for us when we are to plan how to operate a reservoir in the future. Now, what Acht allows you to do is to take a model with uncertainty attached to it, and then basically just spawn a multiverse, a bunch of different universes representing this model, where each and every one of these models is a concrete model with concrete knowledge that you can simulate ahead in time. And by that, you can make forecasts, run simulators, reason about the results, etc. So this allows you to take all of these different universes, simulate them ahead in time, and then use statistics to reason about what you think will happen in this model of yours that has uncertainty. This allows you to say something about the future, but it also allows you over time to compare what you are simulating on the computer with what you are observing in reality. And by doing so, the hope is that you can actually gain improved knowledge of your system. Now, as the name dictates and these examples show, this application was originally made for dealing with uncertainty in reservoir models. But today, we are also using them for our wind farms. We are using Acht to quantify the uncertainty of wind farm models how the turbulence behaves under different weather conditions, and so forth. So basically, if you have something that you can simulate, but where the model itself has some inherent uncertainty, then ART can be your tool. Now, if you think that this sounds really cool, then you're at luck, my friend. Because actually, at NDC TechTown last year, I gave a talk on the mathematics behind ART. So if you want to know more about that, then you can go to YouTube and check out that talk. But today we are to talk about ART as a software project. And started out with reservoirs and the need for software. Someone had an idea, that idea evolved into mathematics, which again was manifested in software that allowed you to reason about this uncertainty. And this was to a large extent developed by a single developer, which is a massive feat, but it also has some interesting consequences that I will get back to later on. So we have users, scientists, geologists, reservoir engineers that start to use this tool to reason about the uncertainty in the physical object that they are modeling. And this actually imposed a pretty big cultural change in the way that they are working, because then suddenly they had to reason not only about the uncertainty of the process that they are doing, but they also had to communicate this to the ones using their results. And furthermore, this uncertainty also had to be communicated to management to really get the best out of these tools. So I imagine that what they faced when communicating this uncertainty is quite similar to what we sometimes face as software developers when we are communicating uncertainty around how long something will take to make what we are making, etc. And to be honest, to give you a bit of hope, it is actually today, as this program has been going for so long, people with the habit of reasoning about uncertainty has also gone up into management. And sometimes, if someone is asking for an estimate because they actually need it to make an informed decision, I sometimes give them probability distribution back, and they are fine with it. And I think that's awesome. So over time, this provided the company with a lot of value because it actually improved our knowledge of reservoirs. So more and more fields started to implement this technology. We got more users needing different features from the software, and the software grew more and more complex. We onboarded more developers to deal with the project, and I have to say that the process was very much feature-driven, which is a good thing because it provided tremendous value to the company. But what it perhaps failed on, to some extent, was to address debt. So debt accumulated in the project in various ways. So for instance, we accumulated quite a bit of technical debt. And as developers, we experience and live in that now, and is dealing with that now. And it basically says something about our ability to move from where we are today to where we want to be. We are slowed down, and we need to pay back and reorganize our software to make it into what both we and our users would like it to be in the future. But even more so, this technical debt is imposing things on our users. So one of the consequences is that they get quite cryptic error messages. And due to not always having coherent feature design, we have actually ended up in a scenario where sometimes one user's feature is another user's bug. And as you saw in the figure, we are to run simulations, but that goes beyond just a single simulator. We also have to take numbers and encode that as a plan in the model. We have to reason about the model afterwards. And a lot of this is happening on the compute cluster. But quite a bit of it also happens on the client side, because we want to reason about across all of these universes. And there is an API for doing this, but it's extremely complicated. So although our users can, in theory, do what they need to do, the complexity and inconsistency of the design of the APIs make very few capable of actually doing it. Another very interesting thing is that the work that our users of this software is doing does in many ways resemble the process of us as software developers. They are suffering from changing context, and they need to be able to focus. They have tremendous insight into the physical object that they are simulating. To me, that is one of the coolest things about this project. It is the enormous amount of knowledge that our users have. But due to that the system is not always so easy to figure out, or that it sometimes gives you strange error messages, what started out as being this vision about how you want to model something or how you wanted to quantify uncertainty suddenly boils down to a cryptic error message that no one understands, and looking in documentation and trying to figure out how to do something. And they lost this idea about how to model something. So although the tool itself is providing a lot of value today, our vision together with our users is that this tool should, to a much larger extent, be a natural digital extension of their workflow. Another very interesting place where we accumulated depth in this project is with respect to the knowledge. As I mentioned earlier, it was to a large extent a single developer that developed this project. And there is this notion of a bus factor of a project, which says something about how many of your developers could be hit by the bus today, and the project would still move on. And that number was quite low. And this has many interesting implications. One being that a lot of this developer's time is tied up to this project, because new features are coming in, users need support, bug fixes, etc. And since there are not that many others to do it, this developer needs to do it. But when you realize that you have a legacy project and you want to deal with it, then if you decide to do that by also scaling up your team, then you probably know that that is going to cost you time in training, which means that you will have less time for development. So even though it might pay off long term, it is a massive investment to grow a team. So you need to pay back by having knowledge concentrated in few individuals. I have a colleague, Oliver Maudal, and he says that the individual learning isn't worth that much. Learning needs to happen on an organization level. And I think that's very much true. And it's something that we should be conscious about every day at work, not only when dealing with legacy software, but every time we are developing something. Now, there is also a different perspective to this. And that is that sometimes we joke that being the only one that can develop something, or being one of the few that can develop something, is really good job security. But I think that is a false premise, because not only is the developer's time tied up to this project, but the success, speed, and pace of this project is also tied up to this developer. And this developer is still just a single developer, or possibly a couple of developers. And there is a limit to how much they can do. So yes, you have a lot of competence about something that might not and there might not be that many that have that competence. But that is still building on the hope that this project will be a success. And it will most likely only be a success if you're able to have a good development process and adapt as your domain is changing, the requirements is changing, maybe the IT infrastructure that you have to run on is changing, and you need to be able to deal with that. Another thing that you have to address, especially if you're growing a team, is that you need to nurture your culture. I think we had a pretty good starting point there in software innovation, but still when you bring in new people, we have grown our team by more than 50%. You still need to make sure that the culture is even maintained, but also improved over time. And this is also an investment to make sure that you're all pulling in the same direction, but also to ensure that every team member feels safe and trusted, so that they can tell you when they know something, say, this is a bad idea, I think we should do something else. Or tell you that, I don't know this, I don't understand what this means, can you please explain it to me? Only by having that kind of culture can you build a team with a lot of knowledge around what you're doing. And I think it's very interesting, this perspective of building a team with different features and strengths. And you don't have to be good at everything, but you should probably be good at something, and it should hopefully be some of the things that you need to do your job. So as you get better, as your team gets better at doing what they are doing, which is probably software development, I think we need to accept that you can't get better at everything simultaneously. And on this thing, I think we can learn quite a bit from sports science, because they have a lot of theory on this. And they have this concept called periodization, where you accept that some features of you as an athlete or your team can't be improved at this point because you want to focus on something else. You might even have to accept that I will get slightly worse at this, but at the expense or to become much, much better at something else. And you can envision it being a bit like a computer game where you have some character, or in this case, a spaceship that has various features. And then you can decide to improve this part of your spaceship, this part of your character. And then as a team, you might have to accept that we can't fix everything at the same time, but we can get much better at this right now, and then we can try to get better at something else afterwards. Now, so when you start dealing with a legacy application, then I really believe that you need to get the foundation right first. And by this I mean that you need to get your deploys right. You need to be able to deploy your software in an automatic fashion, in a reproducible fashion, and in a safe fashion, so that when you make iterations, you're able to get that out to your users. I remember when I started working on this project, then a large fraction of the new versions, deploying them would break the entire system. And I mean, this isn't a live system. Nothing stops up. Our money stream doesn't stop if the software stops up. But we are simulating things on an HPC cluster. And these simulations can take quite a bit of time. And there are iterations on top of these simulations where you're adapting and changing the parameters to your model. So in reality, our users can lose days and days of work if we go down. And sometimes that doesn't bother them that much, just a little bit. But sometimes they are generating statistics that are to go into decision making. And maybe that decision has to be made soon. And then they are not so happy. So we really needed to get our deploys right. and I think you do as well, if you are to deal with legacy software. You also need to spend time caring for your test suite. We were quite lucky. We had a good test suite already, or at least a decent one. But you need to be able to make sure that when you are iterating and changing your software, that the correctness and behavior is still preserved. Otherwise, you will have no chance of being sure that the changes that you are making will also keep the software doing what it should. And I think the last thing that you need to do was very surprising to me. But you need to learn to communicate with your users, especially in a complex domain. There is a tremendous difference between both learning the language of your users and also having them learn a bit of your language, lingo. The effectiveness of that communication is just on a different scale than what you had to begin with. And if you want to get a good description of what you should make, what challenges your users are facing, you have to be able to communicate with them. If not, then you're living in a vacuum. And when you've gotten this down, then you can start looking at the architecture of your system, the different components and their responsibilities. And sometimes the boundaries aren't that well defined. Maybe responsibility might be shared between different components that shouldn't share this responsibility. Maybe everything is talking to everything. There is no good structure. But you need to figure out how it is working and how you need to get a realistic image of the architecture today. And then you need to figure out how you would like it to be in the future. And then you need to start making some first steps towards how you would like it to be. This doesn't say that you should follow this plan or that this doesn't change. You have to adapt as you learn and as you go. But starting without a plan, I think, is really naive as well. And also you have to accept that you might have to go through some hurdles and do some not so pretty solutions on your way towards what you want your solution to be. Sometimes when I talk about legacy software to non-software developers, I compare it to building a road network, and you have like a road with a lot of traffic, and then you are to do something with that road. I don't know, build a roundabout or a traffic light or something, and you need to get the traffic over somewhere else to be able to do this work. So you might have to actually create a temporary road. They do this. They create temporary roads to redirect traffic so that they can do what they were supposed to do and then move the traffic back again. And when you have planned your first steps and figured out what you would like it to be, at least with your current knowledge, then you need to find some components that you can start working on, because you can't do everything at the same time. You need to start somewhere. And there can be many ways of finding out where you should start. It would probably be good to find something that is sort of an easy win, not the most complex part of the system. It can also be about in which parts of your system do you expect changes to be able to make the system that your users want. If you see that our users would really benefit from this kind of feature, and that will happen in this part of the software, then it's much better to start with that part than starting with a part that you don't really foresee changing that much in the upcoming future. So you need to figure out where to start. Then you can start implementing that part of your new system and starting to redirect and utilizing features from that part as it gets made. And it is easy to get lost in this kind of work. So you really need to make sure that the new stuff that you're making is good, has high quality, and allow the developers to make something that, so that they don't lose sight of what good quality is, that they suffer from severe quality fatigue. I'll get back to that later on. And when you start making these changes, you should, as always, encapsulate these in like small deliveries. And hopefully you can make many small deliveries. And you can only do these changes if you already made sure that your test suite is decent. If not, then you will stumble already here. And afterwards, you need to make sure that these small deliveries actually get out to your user. Which means that, and you need to do that often as well, you want each of these small deliveries to actually reach out to your users. And you won't be able to do that without dealing with and ensuring that your deploy system is good. So if you fall in the trap of starting to deal with the code without having the necessary tooling, deploy scripts and tests ready, then that will really come back to bite you. And also you need these deploys to actually get to the users, and to get to the users often. Now, one of the challenges with this, when you're dealing with refactoring and rewriting code and managing legacy systems that you want to modernize, is that many of these changes, at least at the bottom level of your application, might not even hit the users. They should hopefully not even recognize it while you're just starting to pull it apart and figure out how it should be like. So now maybe you need to rethink what your user is. Maybe your user actually is a colleague, a developer in your team that is now consuming your new API, or utilizing a new feature that came up, or a more coherent fashion of interacting with this module. And then you should make sure that your deliveries actually reach out to their development environment, and that you can get feedback. And if you are to get feedback both from the users and from these developers, then you need to have established this language of communication so that you can understand how changes are impacting them, or what kind of features they would like to see in the future, so that you know where you should start addressing the legacy of your system. So you need to get that in place. Also, I have to say that when you're dealing with technical debt and knowledge debt, then there are times, as we mentioned, where you don't necessarily deliver that much new functionality to your users, because you're dealing with the depth of the system. And this really requires a great deal of trust between you as developers, the users, and the product owner. Spending time on nurturing that relationship and understanding their needs and explaining the consequences of the work you do today and what it will enable you to do tomorrow, I think that is a really important conversation to have. Now, as I mentioned earlier, you really do need to manage quality fatigue. If you're operating in a lot of technical debt, you might, over time, to avoid becoming crazy, actually lower your standard of what you think good quality is. When you start strangling your software and making new modules, really make sure that they are as good as you possibly manage to make them right now. You need to create these happy zones, safe places in your project that has maybe even a higher quality than what you hope that the system in total will have. Something that really separates the quality of the new parts from the quality of the old parts. Also, you should really make sure to don't let your colleagues get lost in the wilderness of legacy code. We have something like 1.5 million lines of code in C and Python. And sometimes you start out with something that appears to be an easy problem. And then you start addressing that problem. You disappear down into the code, and at some point you lose track of what's going on. You get so focused on the problem that you're trying to solve that you forget about your implication of what you're doing to the design. Maybe you're imposing changes to the design of the API that makes it less coherent than what it was. Maybe you're adding strange things to the build scripts to avoid the hoops, to get it working, and then you don't realize because you're so focused on the problem that you're trying to solve. And in addition, in Equinor, we have something called playground time. And I think that is also a very useful tool to actually manage quality fatigue. So then you get to spend some time to do something completely different, just learn new techniques and new technologies. And I think it's really important to recognize that both by setting a really good standard in these new parts of the project, as well as doing, for instance, this playground time, that will really help you back into managing the rest of the computer system. Now, to cite Martin Fowler, he says, let's face it, all we are doing is writing tomorrow's legacy software today. And I think that's true. And I think we need to embrace it. And honestly, I think maybe that's even the most positive thing, the most positive view you can have on this. Because if you're not writing legacy right now, then you are most likely writing a software system that over time will not be relevant and then just disappear again. Of course, you will have to manage your debt and improve it and make sure that you can iterate on top of your project in the direction you want it to go in. But I think you also need to embrace that you are writing legacy software right now. I read this quote about growing up some weeks back. I didn't manage to find it again, but it basically boiled down to that becoming an adult is coming to peace with that the people around you are nothing but humans. And I think maybe we need to do the same as developers. We need to realize that the code that you are screaming over today was written with good intentions and maybe even was a very good decision at the time when it was written. But tooling changed. Maybe new solutions came around. We learned more about software design or about interacting with our users. Maybe the domain changed completely, or maybe the idea of their entire IT system changed and you want to do something else. So I see that I have spent a little less time than I was planning to, but I now get to conclude my talk. That is the benefit of being a speaker, then you get to conclude. So we need to leverage that wisely, and that goes for all software projects. If you want to move and get somewhere, then accumulating debt might be the fastest way to get there and the best way to get there. Maybe you should just prototype a feature, see how it goes. Maybe it isn't relevant, who knows? So implement it, get it out, get some feedback, but be sure that you also are aware of that debt and that you manage it. Or let someone on your team dig deep down into some topic that you might think will be relevant for how to solve a problem that you're currently trying to deal with in your team. Let them learn something and figure out how something works, and maybe even implement a solution. But then also be aware that that knowledge gained by that person is currently only living there. So make sure afterwards that that knowledge is then fed back into the rest of the team. It allows you to move quickly, but you also need to mitigate afterwards. Also, if you are dealing with a legacy project, then I will highly encourage you to strangle your Hydra iteratively. It's extremely difficult and maybe even impossible, I would say, to do everything at once. You need to iterate your implementation and make sure that changes that you are doing get to your users in a good fashion. And then you can iterate on top of that again afterwards. And last, realize that the code that you are writing today is the legacy of tomorrow, and make that legacy the best you can. I think that we have quite a tendency to be aware of abstractions when we are designing software. We try to do this, of course, they start leaking over time, and maybe it shifts as the domain evolves and so forth. I think we as a community try to do that quite well today. But I personally feel that we sometimes today let the architecture leak too far into our software solutions. I'm not saying that shouldn't happen, because that's what architecture decisions are. We're making big fundamental decisions for your software project. It will, by its very nature, be costly to change. But that doesn't mean that you have to let it flow into every single piece of your code. So I think that is something that I hope we as a community will find even better ways of dealing with, even in a cloud-native kind of architecture in the future. And last but not least, this app project is actually open source, so you can check it out. I think that is also one of the things that you need to embrace when dealing with legacy code. I mean, it is legacy because it provides a lot of value, so that's really, really cool. And also you have to identify with the direction of the project and what is currently going on. And by making that very good, the direction of your project, if you then also in addition apply time, then in the end, you will be able to make an impact on the state of your project. And that is what I have to say. Thank you for listening. And yeah, feel free to shoot questions.